Our universe is a puzzle with countless missing pieces. For centuries, scientists have worked to fill in the gaps, but the picture remains incomplete. We've mapped galaxies, detected gravitational waves, and photographed black holes. Yet these discoveries have only led to more questions. Join us today as we delve into everything we don't know about the universe. The concept of what came before the Big Bang intrigues many, yet it also presents a significant challenge to our understanding of time and space. The Big Bang, occurring approximately 13.8 billion years ago, marks the inception of our universe as we know it, leading to the expansion of space, time, and matter. However, the nature of reality prior to this event is shrouded in mystery, as standard models of physics struggle to describe a time when the universe did not exist. Some theories suggest that before the Big Bang, the universe could have been in a singular state, an infinitely dense point where conventional physics breaks down. Others propose that our universe emerged from a previous cosmic event, or could be the latest iteration in an infinite cycle of expansions and contractions. In this cyclic model, the universe undergoes a series of Big Bangs and Big Crunches, where after each contraction it experiences another expansion. Another fascinating idea is the multiverse theory, proposing the existence of multiple, perhaps infinite universes, each with its own unique laws of physics. Under this perspective, our Big Bang could simply be one event among countless others, occurring simultaneously in a vast and varied cosmos. Each universe within this multiverse might have a different origin, leading to entirely different configurations of matter and energy. These theories highlight the limits of our current understanding and the complexity of the cosmos. While we may not possess definitive answers to what preceded the Big Bang, the exploration of these ideas fuels the journey of scientific inquiry, urging us to look beyond the boundaries of our universe and question the very fabric of existence. The question of why the Big Bang occurred continues to puzzle scientists and cosmologists as it delves into the deepest mysteries surrounding the origins of our universe. The Big Bang theory is widely accepted as the best explanation for the initial expansion of the universe, but it does not provide a definitive answer about the underlying cause of this monumental event. The circumstances that led to the Big Bang remain largely speculative and are the subject of ongoing research. One popular idea within cosmology is that quantum fluctuations in a vacuum could have given rise to the Big Bang. In the realm of quantum physics, fluctuations can occur even in empty space, where particles and antiparticles may appear and then annihilate each other in a fleeting moment. Theories in this domain suggest that a significant fluctuation might have triggered a rapid expansion, leading to the formation of our universe. This process could provide insight into how the fabric of space-time itself may have evolved. Another perspective focuses on concepts such as cosmic inflation. This theory posits that a brief exponential expansion followed the initial singularity, smoothing out irregularities and setting the stage for the universe we observe today. While inflation explains how the universe expanded rapidly just after the Big Bang, it does not address the fundamental question of why the Big Bang happened in the first place. Many cosmologists also consider the possibility of a pre-existing state or alternate framework in which our universe exists. This approach may suggest that our universe is just one of many that emerged from an intricate interplay of physical laws beyond our current understanding. While much research remains to be done, exploring these questions is crucial for grasping the origins of everything we know and the overarching structure of reality itself. The emergence of the laws of physics from the Big Bang is a profound aspect of our understanding of the universe. At the moment of the Big Bang, approximately 13.8 billion years ago, the universe was in an extremely hot and dense state. It was during this early period, known as the Planck era, that the fundamental forces of nature began to take shape. These forces include gravity, electromagnetism, and the strong and weak nuclear forces, which are the cornerstones of modern physics. As the universe expanded and cooled, the fundamental particles that constitute matter began to form. Initially, the universe was a chaotic soup of quarks and gluons. However, as temperatures dropped, quarks combined to form protons and neutrons, signaling the onset of what we might consider the building blocks of matter. This phase transitions into the formation of atomic nuclei during nuclear synthesis, which occurred a few minutes after the Big Bang. The subsequent cooling allowed electrons to join with protons and form neutral hydrogen atoms, leading to the creation of the first atoms. which would later combine to form stars and galaxies. The laws of physics, as we perceive them, stem from symmetries and conservation principles that govern these fundamental forces and particles. For example, the theory of quantum mechanics and the theory of relativity play pivotal roles in determining how particles interact and how gravity operates on a cosmic scale. The unification of these forces into coherent laws is a field of ongoing research, particularly in the quest to formulate a grand unified theory that can describe all forces under a single framework. While we have made substantial advancements in understanding how the laws of physics emerged and operate, many questions remain. The early universe's conditions were so extreme that they defy our current physical theories. Events such as the unification of forces and the behavior of matter and energy at such high energies necessitate new theories. Grasping these complexities not only deepens our comprehension of the cosmos, but also invites us to explore the very foundation upon which reality is constructed. The initial imbalance between matter and antimatter is one of the most intriguing puzzles in modern cosmology and particle physics. According to the laws of physics, for every particle of matter, there should exist a corresponding particle of antimatter which is identical in mass but opposite in charge. In the moments following the Big Bang, it is believed that equal quantities of both matter and antimatter were created. Nevertheless, our universe is dominated by matter, with only trace amounts of antimatter detectable today. One possible explanation for this imbalance lies in a phenomenon known as baryogenesis. This concept refers to the processes that may have led to an excess of baryons, the family of particles that includes protons and neutrons, over antibaryons. Various theories suggest conditions in the early universe that could have favored the production of matter over antimatter. For instance, certain interactions and decay processes might allow for the violation of symmetries, specifically a property called charge parity violation. This indicates that the laws of physics could behave differently for matter and antimatter under specific conditions. Experiments, particularly those involving particle accelerators, have been vital in identifying CP violation. Observations of certain decays involving particles called kaons and B-mesons demonstrate that these violations exist, suggesting that they could contribute to the slight excess of matter. However, these observed effects alone cannot account for the vast disparity required to explain why our universe is largely composed of matter. Another avenue of research explores the role of inflationary theory, which proposes a rapid expansion of the universe shortly after the Big Bang. During this phase, any remaining antimatter could have been diluted or driven apart from matter due to inhomogeneities in the distribution of energy in matter, leading to regions dominated by matter. As we delve deeper into these concepts, we edge closer to unraveling the mystery of the asymmetry that shapes the cosmos and ultimately defines the very nature of our existence. The formation of the first atoms in the early universe is a fascinating process that unfolded during a period known as recombination. This event occurred roughly 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. Prior to this era, the universe was an incredibly hot and dense plasma composed primarily of quarks, gluons, protons, neutrons, and electrons, making it opaque to radiation due to frequent interactions among particles. As the universe expanded, it gradually cooled. When the temperature dropped to about 3000 Kelvin, electrons were able to combine with protons without being immediately ripped apart by high-energy photons. This process of recombination allowed for the formation of the first stable hydrogen atoms. Once these atoms were formed, the universe became transparent to radiation, leading to the release of the cosmic microwave background radiation, which we now detect as an echo of this primordial event. In addition to hydrogen, a small fraction of helium was formed during nucleosynthesis, which took place within the first few minutes of the universe's existence. In this process, protons fused to create helium nuclei alongside trace amounts of lithium and beryllium. Most of the universe's helium was created during this nucleosynthesis phase rather than through subsequent stellar processes. The emergence of these first atoms marked a critical point in cosmic history. Not only did this transition lead to the universe becoming transparent and enabling the formation of light, but it set the stage for the subsequent development of stars, galaxies, and the intricate structures we observe today. As stars formed, they fused hydrogen into heavier elements, enriching the universe with the variety of elements that are essential for life as we understand it. This process highlights the remarkable journey from the simplicity of a hot plasma to the complex, structured universe we inhabit many billion years later. The nature of dark matter remains one of the most perplexing questions in contemporary astrophysics. Dark matter is an invisible substance that does not emit or absorb light, making it impossible to detect directly through conventional means. Its existence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Approximately 27% of the total energy density of the universe is attributed to dark matter, yet its composition continues to elude scientists. One of the leading candidates for dark matter is a category of hypothetical particles called weakly interacting massive particles, or WIMPs. These particles are predicted to have mass but interact only through the weak nuclear force and gravity, making them extremely difficult to detect. Various experiments are ongoing to find evidence of WIMPs using underground detectors, particle accelerators, and other advanced technologies. If discovered, WIMPs could provide crucial insights into the true nature of dark matter. Another potential candidate is axions, extremely lightweight particles that might also account for dark matter. Axions are predicted by certain theories of particle physics and could generate weak signals detectable by specialized experiments. Like WIMPs, axions would have only minimal interactions with ordinary matter, making them hard to identify. The search for axions involves innovative techniques, including the use of strong magnetic fields to convert their hypothetical presence into detectable photons. Current research also considers alternatives to particle candidates. Some theories propose that dark matter might be related to modifications in gravitational theory itself, such as modifications to Einstein's general relativity. These alternative explanations challenge the traditional view of dark matter and open the door to new physics. The quest to uncover the true nature of dark matter not only promises to deepen our understanding of the cosmos, but may also redefine our grasp of fundamental physics. As experiments continue, the answers could revolutionize our comprehension of the universe and the mysterious forces that govern it. The inability to directly observe dark matter is rooted in its unique properties that differentiate it from ordinary matter. Dark matter does not emit, absorb, or reflect light or any other form of electromagnetic radiation, which makes it invisible to the conventional means of observation that astronomers typically employ. Our telescopes and instruments, which are adept at detecting various forms of light, simply cannot perceive anything that does not interact with electromagnetic forces. The nature of dark matter suggests that it primarily interacts through gravity. While ordinary matter clumps together and forms stars, planets, and galaxies, dark matter forms a framework around which visible matter organizes. This gravitational influence can be observed through phenomena such as the rotation curves of galaxies, where stars on the outskirts move faster than expected based on the visible mass alone. Additionally, dark matter's presence can be inferred from the gravitational lensing of light from distant objects, which reveals the curvature of space caused by its mass. These observations allow scientists to map the distribution of dark matter without actually seeing it. Furthermore, current theoretical models propose that dark matter might consist of particles that interact very weakly with regular matter. This weak interaction makes it challenging for experimental setups designed to detect these particles to succeed. Various experiments are attempting to identify potential dark matter candidates, such as weakly interacting massive particles and axions, but they require precise conditions and sophisticated technologies to create or detect the elusive signals these particles might produce. The quests for understanding dark matter emphasize the limitations of our observational tools and the necessity for innovative approaches to physics. As we continue exploring the universe and refining our technology, the hope remains that we will one day pierce the veil of darkness that surrounds this enigmatic substance and reveal its profound implications for the cosmos. Dark matter interacts with regular matter primarily through gravity, which is fundamentally different from how ordinary matter interacts with itself. While regular matter exerts electromagnetic forces allowing atoms to bind together and form complex structures, dark matter's interactions are solely gravitational. This means that, although dark matter may not be directly visible or detectable through light, its gravitational influence is significant and can be observed in various cosmic phenomena. The effects of dark matter on regular matter can be seen in the behavior of galaxies. When astronomers measure the rotation speeds of stars in galaxies, they observe that stars on the edges rotate much faster than what would be expected based on the visible mass. This discrepancy indicates that there is likely a significant amount of unseen mass attributed to dark matter exerting gravitational pull on the stars. This phenomenon led to the realization that dark matter constitutes a considerable portion of the overall mass within galaxies, helping to hold them together. Moreover, dark matter also plays a crucial role in the large-scale structure of the universe. It forms a scaffolding of gravitational wells that facilitates the formation of galaxies and galaxy clusters. As matter clumps under the influence of gravity, dark matter provides the necessary gravitational pull to aid in the collapse of gas and dust into stars and galaxies. This interplay between dark matter and regular matter shapes the cosmic web, influencing the distribution of galaxies across vast distances. Current research also explores the possibility of other forms of interaction between dark matter and regular matter. Some theories suggest that there might be additional, albeit extremely weak, interactions through forces beyond gravity, although these have not yet been confirmed. Investigating these potential interactions could redefine our understanding of both dark matter and the fundamental forces of nature. The ongoing pursuit of this knowledge sheds light on the complex relationship between dark matter and the visible universe, revealing the intricate mechanisms fueling cosmic evolution. The accelerating expansion of the universe, initially surprising to scientists, is primarily attributed to a mysterious phenomenon known as dark energy, discovered through observations of distant supernova. In the late 1990s, this acceleration suggests that the rate at which the universe is expanding is not just increasing, but doing so at an ever-accelerating pace. Dark energy is believed to constitute about 73% of the total energy density of the universe, yet its exact nature remains elusive. One of the leading theories regarding dark energy posits that it is a constant energy density inherent to the fabric of space itself, often referred to as the cosmological constant. This idea originates from Einstein's equations of general relativity, which originally included a term to account for a static universe. When it was found that the universe was expanding, this term was discarded. However, the discovery of the universe's acceleration revived interest in this concept, suggesting that as space expands, more dark energy is created, perpetuating the acceleration. Another possibility is that dark energy could represent a dynamic field that changes over time rather than being a constant value. This leads to alternative theories such as quintessence, which suggests that dark energy may have varying energy density at different epochs of cosmic history. Such models offer a broader perspective on how the universe evolves and how dark energy might influence its ultimate fate. The implications of the accelerating expansion are profound and raise fundamental questions about the future of the universe. If dark energy continues driving the acceleration, it may lead to scenarios like the Big Freeze, where galaxies drift ever farther apart, ultimately leaving a cold, empty cosmos. The search for understanding dark energy remains one of the biggest challenges in modern cosmology. As research continues, unlocking the secrets of dark energy could reshape our comprehension of the universe and the underlying physics that governs its evolution. The nature of dark energy, whether it is constant or changes over time, remains a significant question in cosmology. The simplest model of dark energy is known as the cosmological constant, which posits that dark energy has a uniform energy density throughout space and time. This concept was initially introduced by Albert Einstein in 1916 as part of his theory of general relativity. When it was later determined that the universe was expanding, the cosmological constant was largely abandoned, only to be revived upon the discovery of the universe's accelerating expansion. Under the cosmological constant model, dark energy does not change. It remains constant as the universe expands. This simplicity makes it an attractive explanation, as it provides a straightforward way to account for the observed acceleration in cosmic expansion. In this scenario, as space expands, the energy density of dark energy contributes increasingly to the overall dynamics of the universe, leading to continued acceleration. However, alternative theories suggest that dark energy could indeed vary over time. One such idea is quintessence, which posits a dynamic field with an energy density that changes according to the state of the universe. In this model, dark energy would exhibit different properties at various stages of cosmic history, potentially influencing the rate of expansion and even allowing for some interaction with matter. This variability adds complexity, but could help explain certain observations that remain unexplained by the cosmological constant theory. Current observations and data collection, such as galaxy clustering surveys and measurements of the cosmic microwave background radiation, are crucial in determining the true nature of dark energy. As cosmologists continue to refine their models and gather new insights, clarity regarding whether dark energy is constant or dynamic could significantly enhance our understanding of the evolution and ultimate fate of the universe. Ultimately, unraveling the mysteries of dark energy may provide fundamental insights into the underlying structure of the cosmos. Yes, there are several alternative theories and models that attempt to explain galaxy rotation curves without invoking dark matter. The compelling evidence for dark matter arises from the observation that stars at the outer regions of galaxies rotate at speeds that cannot be accounted for by the visible mass alone. Various alternatives seek to explain these phenomena through different mechanisms. One notable alternative is modified Newtonian dynamics, commonly referred to as MOND. Proposed by physicist Mordechai Milgrom in the early 1980s, this theory modifies Newton's laws of gravity to account for the observed rotation curves of galaxies. According to MOND, at very low accelerations, such as those found at the edges of galaxies, gravity behaves differently than what Newton's laws predict. By altering the equations governing gravity, MOND can replicate the flat rotation curves seen in galaxies without needing additional unseen mass. While MOND has been successful in some observational cases, it struggles with broader applications, such as explaining the dynamics of galaxy clusters or the cosmic microwave background. Another alternative involves the concept of self-interacting dark matter. While this still includes dark matter in the equation, it proposes that the interactions among dark matter particles could reduce the need for large amounts of unseen mass to explain rotation curves. If dark matter particles collide with each other, this could lead to different dynamics, for example, generating enough friction to alter the expected paths of stars within galaxies. Researchers are investigating whether self-interacting dark matter could bridge the gap between the need for dark matter and the observed properties of galaxies. Other theories include modified gravity models, such as Multiverse or fifth force theories, which suggest the existence of additional forces at play. These concepts often seek to refine our understanding of how gravity operates on cosmic scales without requiring dark matter. While these alternative explanations present intriguing possibilities and merit investigation, the substantial evidence supporting dark matter, including observations of gravitational lensing and cosmic structure formation, has kept it at the forefront of cosmological theories. The discourse on these alternatives continues as researchers seek to reconcile observations with the fundamental physics of the universe. Dark energy is believed to be uniformly distributed throughout the universe, unlike ordinary matter, which clumps together to form stars, galaxies, and other structures. This uniform distribution implies that dark energy does not aggregate in the same way that visible matter does. Rather, it exerts a consistent but subtle influence on the fabric of space-time across vast distances. As the universe expands, the volume of space increases. Dark energy is theorized to exist as a constant energy density that fills this expanding space. This means that as new space is created through the expansion, an equivalent amount of dark energy is also added. In this framework, the overall energy density of dark energy remains constant, even as the universe grows. This characteristic is one reason why dark energy is a compelling explanation for the accelerating expansion of the universe as its effects become more pronounced over larger scales. Some models propose that dark energy might not be as constant as traditionally thought. For instance, in theories like quintessence, the energy density of dark energy can vary with time and spatial location. Such models suggest that dark energy could change over the course of cosmic evolution, potentially leading to different behaviors in the expansion rate of the universe at various epochs. However, these variations must still be compatible with existing observational data, which currently supports the idea of a relatively constant distribution of dark energy. Ultimately, while dark energy appears to be uniformly spread throughout the cosmos, its exact nature and properties remain active areas of research. Ongoing studies aim to refine our understanding of how dark energy behaves and its role in the universe's future. As observations improve and new data emerges, we may gain greater insights into the subtleties of dark energy's distribution and its impact on cosmic expansion and structure formation. The search for dark matter extends beyond Earth-based experiments and into space. Satellites and space-based observatories play a crucial role in mapping the distribution of dark matter across the cosmos. By studying the gravitational effects on light from distant galaxies, scientists can create detailed maps of dark matter concentrations. These cosmic maps reveal a web-like structure, with dark matter forming the scaffolding upon which visible matter congregates. Understanding this large-scale structure is vital for comprehending how the universe evolved and how galaxies formed. The interplay between dark matter and ordinary matter in galaxy formation is a topic of intense study. Computer simulations suggest that dark matter halos form first, creating gravitational wells into which normal matter falls. This process leads to the formation of stars and galaxies within these dark matter cocoons. However, discrepancies between simulations and observations, such as the cuspy halo problem and the missing satellite problem, continue to challenge our understanding of dark matter's role in galactic evolution. Resolving these issues could provide crucial insights into the nature of dark matter and its interactions. Dark energy's influence extends beyond just accelerating the universe's expansion. It also affects the growth of cosmic structures. As the universe expands more rapidly due to dark energy, it becomes increasingly difficult for gravity to pull matter together to form new galaxies and clusters. This means that in the far future, as dark energy's effects become more dominant, the formation of new cosmic structures may slow down or cease entirely. Understanding this process is crucial for predicting the long-term evolution of the universe and its ultimate fate. The quest to understand dark energy has led to the development of new observational techniques and ambitious projects. One such endeavor is the study of baryon acoustic oscillations, BAO, which are periodic fluctuations in the density of visible matter in the universe. By measuring these oscillations at different cosmic epochs, scientists can track how the universe's expansion rate has changed over time, providing valuable data on dark energy's properties. Future missions and telescopes are being designed specifically to study BAO and other dark energy-related phenomena with unprecedented precision. Future missions and telescopes are being designed specifically to study BAO and other dark energy-related phenomena with unprecedented precision. The potential connection between dark matter and dark energy remains an intriguing area of research. While currently treated as separate phenomena, some theories propose a link between the two. These unified dark fluid models suggest that dark matter and dark energy might be different aspects of the same underlying substance. While speculative, such theories highlight the possibility of a deeper connection between these mysterious components of the universe. Exploring these potential links could lead to a more comprehensive understanding of the cosmos and possibly reveal new fundamental physics. The implications of dark matter and dark energy extend beyond astrophysics and cosmology, influencing our understanding of particle physics and the nature of space-time itself. The search for dark matter particles has led to advancements in detector technology and pushed the boundaries of our understanding of particle interactions. Similarly, investigations into dark energy challenge our concepts of vacuum energy and the fundamental properties of space. These pursuits may ultimately lead to a revolution in physics, potentially unifying our understanding of the very large, cosmology, and the very small, quantum mechanics. As our knowledge of dark matter and dark energy evolves, so too does our appreciation of the universe's complexity. These enigmatic components remind us that the cosmos is far stranger and more mysterious than we once imagined. They challenge our assumptions and drive us to explore new realms of physics and astronomy. As research continues, each new discovery not only brings us closer to understanding these phenomena, but also often raises new questions, ensuring that the pursuit of knowledge in this field remains dynamic and exciting. The center of a black hole, often referred to as the singularity, is a region where the gravitational pull becomes so intense that the laws of physics as we currently understand them break down. At this point, matter is thought to collapse into an infinitely dense state, and space-time curvature becomes extreme. The singularity is hidden from the outside universe by the event horizon. the boundary beyond which nothing, not even light, can escape. Within this central core, all known physical theories, including general relativity, struggle to provide satisfactory answers. General relativity posits that gravitational forces can significantly warp space-time, and this warping intensifies as one approaches the singularity. The conventional laws governing particles and forces cease to operate in ways we can measure or predict. The consequence of this breakdown presents a significant challenge for physicists, as reconciling general relativity with quantum mechanics remains one of the most important unresolved issues in modern theoretical physics. In the context of a black hole, particularly a rotating one known as a Kerr black hole, the singularity may take on a ring-like shape rather than a point. This configuration, combined with the extreme warping of space-time, complicates our understanding of what occurs in this region. Additionally, the presence of other phenomena, such as Hawking radiation, theorized by physicist Stephen Hawking, suggests that black holes can slowly evaporate over time, leading to questions about the fate of information that falls into a black hole. Further exploration into understanding what happens at the center of a black hole may require new physics that unites general relativity with quantum mechanics, often referred to as quantum gravity. As researchers continue to investigate the mysteries of singularities, revelations about their nature may not only reshape our understanding of black holes, but could also provide deeper insights into the fundamental workings of the universe itself. The question of whether information is destroyed in a black hole is a profound and contentious topic in theoretical physics, sparking considerable debate over the nature of black holes and the fundamental principles of quantum mechanics. According to classical interpretations of black hole physics, once matter and information cross the event horizon, they seem to be lost to the outside universe, leading to a scenario often referred to as information loss. This idea raises serious implications for the conservation of information, which is a cornerstone of quantum mechanics. This dilemma gained significant attention with Stephen Hawking's discovery of black hole radiation, which suggests that black holes can emit radiation and gradually lose mass over time. If a black hole could completely evaporate due to Hawking radiation, then any information about the matter that fell into it would appear to vanish as well. This notion created what is now known as the black hole information paradox, which challenges the principles of quantum mechanics that assert information cannot be destroyed. In the years since, various proposals have emerged to resolve this paradox. One prominent idea suggests that information is not lost but rather encoded in the Hawking radiation itself. According to this perspective, while the information may seem to be inaccessible once inside the black hole, it could eventually be released as the black hole evaporates. In this way, the total information remains preserved, even if it takes a vastly complex form. Researchers like Juan Maldacena have explored holographic principles, indicating that information about the internal states of a black hole may be retained on its event horizon. Another development in this discourse is the idea of black hole complementarity, which posits that observers falling into a black hole and those outside the event horizon may have different descriptions of physical processes, yet these descriptions are equally valid. This concept suggests a deeper structure to space-time and emphasizes our incomplete understanding of black hole physics. As ongoing research, including advancements in quantum gravity and string theory, progresses, the question of information conservation remains a high priority in theoretical physics. Ultimately, resolving whether information is destroyed in a black hole could lead to monumental shifts in our understanding of fundamental laws governing the universe. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way, where their masses can reach millions or even billions of times that of our Sun. The exact process of how these colossal entities form is still an area of active research, but several leading theories provide insight into their origins. One widely accepted idea suggests that supermassive black holes begin as smaller black holes formed from the remnants of massive stars that have undergone gravitational collapse. After a massive star exhausts its nuclear fuel, it can no longer support itself against gravity and collapses, often resulting in a supernova explosion. The core that remains can become a black hole. These smaller black holes can then merge with each other in dense star clusters, gradually accumulating mass over time. Another intriguing possibility involves the direct collapse of massive gas clouds in the early universe. During the time of the first stars, gas clouds could have collapsed directly into one or more black holes without forming a star first. This material would rapidly gain mass, potentially becoming supermassive, solidifying their enormous size from an early point in cosmic history. Additionally, supermassive black holes could play a key role in the evolution of their host galaxies. As they grow, they create immense gravitational pull, influencing the motion of stars and gas in their vicinity. The interplay between black holes and galactic dynamics leads to a fascinating relationship that continues to shape our understanding of the universe's structure and development. With ongoing advancements in observational technology, researchers hope to unveil more about these cosmic giants and their formation pathways. The event horizon of a black hole is often described as the boundary beyond which nothing can escape the black hole's gravitational pull, not even light. This makes it an incredibly mysterious region in our understanding of the cosmos. However, what lies beyond this point remains a subject of much speculation and scientific inquiry. Once an object crosses the event horizon, current scientific theories suggest that it is inexorably drawn toward the singularity at the center of the black hole. A singularity is a point where gravitational forces compress matter to infinite density. Here, the laws of physics as we currently understand them begin to break down. The fabric of spacetime is thought to curve infinitely, presenting challenges for physicists trying to reconcile general relativity with quantum mechanics. The nature of the singularity raises many intriguing questions. For instance, does time behave differently in this extreme gravitational field? While the outside universe continues its progression, for an observer who crosses the event horizon, time would appear to advance normally until they reach the singularity, where both time and space lose their conventional meanings. Some theories postulate that the interior of a black hole could possess alternative realities or parallel universes, sparking fascination and debate in the scientific community. While current black hole models do not provide concrete answers about what happens beyond the event horizon, ongoing research and theoretical advancements may eventually bring us closer to unraveling the mysteries hidden within these cosmic enigmas. The concept of harnessing energy from rotating black holes, specifically those known as Kerr black holes, is a fascinating idea that exists at the intersection of physics and theoretical speculation. These black holes not only possess mass, but also angular momentum due to their rotation, which opens up intriguing possibilities for extracting energy from their dynamics. One proposed method for energy extraction is known as the Penrose process, named after physicist Roger Penrose. According to this theory, it is possible to send an object into the black hole's ergosphere, a region outside the event horizon where space-time is dragged around by the rotating black hole. Inside the ergosphere, an object can be split into two parts. One part can fall into the black hole, while the other escapes with greater energy than the original object. This process could, in principle, result in the extraction of rotational energy from the black hole, although the practical implementation of this process remains firmly in the realm of theoretical physics. Another way to conceptualize energy extraction is through the concept of Hawking radiation, proposed by Stephen Hawking. This phenomenon suggests that black holes could emit radiation due to quantum effects near their event horizons. Although this radiation is generally infinitesimally small for large black holes and presents significant challenges for collection, it raises the possibility of black holes gradually losing mass over astronomical timescales, potentially providing energy in the far future. While these concepts sound promising from a theoretical perspective, practical applications of harnessing energy from black holes remain highly speculative. Current technology and understanding of black holes do not yet allow us to exploit these immense gravitational entities in any substantial way. Nonetheless, the exploration of such ideas enhances our understanding of extreme physics and inspires imaginations about the potential for future energy sources in an advanced civilization. Binary black hole systems, formed when two black holes are gravitationally bound to each other, provide fascinating insights into the dynamics of gravitational interactions. The evolution of these systems is a complex dance influenced by various factors, including their masses, spins, and the surrounding environment. As these black holes orbit one another over time, they can lose energy through the emission of gravitational waves. These ripples in space-time are produced by the accelerating masses of the black holes as they move in their elliptical orbits. The emission of gravitational waves carries away energy, causing the black holes to gradually spiral inward. This process is relatively slow initially, taking millions or even billions of years, but it accelerates significantly as the black holes get closer together. When the black holes finally approach very close proximity, they enter a phase known as the merger. During this event, a dramatic burst of gravitational waves is released, which can be detected by instruments like LIGO and Virgo. This merger event signals the transformation of two separate black holes into a single, more massive black hole. During the final moments, massive amounts of energy are released, and the characteristics of the resulting black hole can vary based on the initial spins and masses of the original black holes. The aftermath of the merger contributes to the growth of supermassive black holes at the centers of galaxies and informs models of galaxy evolution. In addition, these binary systems are crucial for understanding the nature of gravity and the fabric of spacetime itself. With advancements in technologies to detect gravitational waves, our understanding of binary black hole evolution continues to evolve, revealing the intricacies of some of the universe's most powerful phenomena. The final moments of a black hole's evaporation, a process predicted by the theory of Hawking radiation, are among the most enigmatic and thought-provoking phenomena in modern physics. Over astronomical timescales, black holes lose mass by emitting particles through quantum effects near their event horizons. This slow radiation results from the virtual particles that constantly pop in and out of existence in the vacuum of space. As a black hole evaporates, it goes through a gradual decline in mass. But during the final moments, something extraordinary occurs. The rate of emission of Hawking radiation increases dramatically, leading to a rapid decrease in mass. As it shrinks, the black hole becomes hotter, and its emitted radiation becomes more intense. This last phase is often conceptualized as a sort of cosmic explosion, as the energy density reaches extraordinary levels just before the black hole dissipates completely. During this climactic stage, the black hole may emit bursts of high-energy particles, including photons and other fundamental particles. This final outpouring could potentially release an enormous amount of energy, whispering away the last remnants of the black hole into the surrounding space. If this particle's emission were to occur within a stellar environment, it might provide insights into how stellar remnants interact with their surroundings during this transformative phase. Importantly, the information paradox arises in these final moments, questioning whether the information about the matter that fell into the black hole is destroyed or retains some form of accessibility after evaporation. This paradox remains one of the open questions in theoretical physics, captivating researchers and driving investigations into the fundamental nature of information in the universe. As scientists continue to study black holes and their evaporation, we may gain deeper insights into the realms of quantum mechanics and the fabric of spacetime itself. The true shape of the universe is one of the most profound questions in cosmology, and it closely relates to the underlying geometry of spacetime itself. The current understanding suggests that the universe can be described using different geometrical models that depend on the average density of matter and energy it contains. One possible shape is flat, resembling a sheet of paper. In a flat universe, parallel lines would never meet, and the overall geometry would follow the rules of Euclidean geometry. Observations, particularly those from the cosmic microwave background radiation, indicate that the universe appears very close to flat on a cosmic scale, suggesting that the total density of matter and energy is nearly equal to the critical density needed to achieve this geometry. Another scenario proposes a closed universe, akin to the surface of a sphere. In this model, the universe would be finite but unbounded. If you were to travel in a straight line in a closed universe, you would eventually return to your starting point. The curvature of space would mean that geometric rules diverge from our familiar Euclidean intuitions, leading to phenomena like the potential for a big crunch, where the universe might eventually collapse back on itself. Conversely, an open universe resembles a saddle shape, where parallel lines would eventually diverge. This model implies that the universe could expand indefinitely without returning to a previous configuration. Each model has distinctive implications for the ultimate fate of the universe and the behavior of light and objects within it. In addition to these classical models, the universe's shape can be influenced by dark energy, a mysterious force driving its accelerated expansion. Understanding the true shape of the universe remains an active area of research, with ongoing observations and studies seeking to refine these models. As we delve deeper into the cosmos and gather more data, Scientists continue to piece together the intricate puzzle of our universe's structure and its cosmic destiny. Yes, there are indeed structures in the universe that exceed the scale of galaxy superclusters, which are already vast collections of galaxies held together by gravity. One of the largest known structures is called a cosmic filament, which is a part of the large-scale structure of the universe. These filaments consist of immense threads of galaxies and dark matter, forming a vast web-like structure that spans hundreds of millions of light-years across. The largest of these structures are often referred to as superclusters of superclusters. An example is the Laniakea supercluster, which contains the Milky Way and is itself a part of an even larger network of galaxy clusters and filaments. Within this web, clusters and superclusters group together in a way that indicates the complex gravitational influences at play across cosmic scales. Beyond cosmic filaments, there are also structures called voids. Voids are enormous, relatively empty regions of space surrounded by filaments and clusters of galaxies. These voids can stretch for hundreds of millions of light-years and represent some of the largest unoccupied areas in the universe. The interplay of dense regions filled with galaxy clusters and these vast voids helps to shape the overall structure of the cosmos. As astronomers employ advanced observational technologies, they continue to uncover the complexity and scale of the universe's architecture. The hierarchical nature of cosmic structures, from galaxies to superclusters and beyond, paints a fascinating picture of how gravity and dark matter have sculpted the universe over billions of years. Each discovery furthers our understanding of the universe's large-scale structure and the underlying forces at play. The formation of the first galaxies is a key event in cosmology, occurring roughly at the end of the cosmic dark ages, around billions of years after the Big Bang. During this time, the universe was cooling and expanding, creating conditions conducive to the formation of matter. The initial moment saw a uniform expanse of gas, primarily composed of hydrogen and helium, but gravitational instabilities began to disrupt this uniformity. As tiny fluctuations in density occurred, regions with slightly more matter began to attract additional gas. Over time, these regions collapsed under their own gravity, leading to the creation of the first star clusters. These primordial stars were likely massive and short-lived, burning brightly before exploding as supernova. The explosion enriched their surroundings with heavier elements, facilitating the formation of subsequent generations of stars and, eventually, galaxies. The process of galaxy formation was not uniform. Some regions experienced rapid star formation, leading to the creation of small galaxies that merged over time. This merging process allowed for the buildup of larger and more complex structures. The role of dark matter is crucial here, as it provides the gravitational scaffolding necessary to capture and hold regular matter, influencing how galaxies clustered together. As these early galaxies continued to evolve, they began to establish the framework for the galaxies we observe today. Their behavior shapes the large-scale structures of the universe and influences the formation of the cosmic web we see in the present. Understanding how these first galaxies formed and evolved is fundamental to unraveling the history of the universe and our place within it, making it an essential area of inquiry for astronomers and cosmologists alike. The filamentary structure of the cosmic web arises from gravitational interactions on a vast scale, shaping the distribution of galaxies, galaxy clusters, and dark matter throughout the universe. This intricate arrangement is a result of the fundamental laws of gravity, working over billions of years to create a vast network that interconnects all visible matter. In the early universe, matter was primarily distributed uniformly, but quantum fluctuations from the inflationary period created tiny density variations in the primordial gas. Over time, these small fluctuations intensified due to gravitational attraction, leading to the formation of regions with higher density. Galaxies and clusters began to form in these dense areas, while less dense regions expanded. This uneven distribution of matter eventually led to the emergence of a network of filaments and nodes. The filaments themselves are composed mainly of dark matter and are often surrounded by a hot gas. Dark matter, which makes up a significant portion of the universe's mass, does not emit light and remains invisible, yet it exerts a gravitational influence that guides the motion of visible matter. As galaxies and clusters drift through space, they tend to move toward these filamentary structures, which act as highways for cosmic matter, drawing galaxies together through gravitational attraction. This web-like configuration creates a striking contrast with vast voids, which are expansive regions of space with comparatively few galaxies. The energy dynamics and gravitational influences within these filaments help explain the large-scale structure of the universe as we observe it today. Ongoing research, including simulations and observations, continues to enhance our understanding of how these cosmic webs form and evolve, revealing the underlying forces that shape the universe on the grandest scales. Voids in the universe are vast, relatively empty regions containing far fewer galaxies than typical areas of space. Their existence is deeply rooted in the mechanics of cosmic evolution and the gravitational dynamics that shaped the large-scale structure of the universe. Understanding why these voids form involves investigating the fundamental processes that govern the distribution of matter and energy. At the earliest stages of the universe, matter was distributed relatively uniformly, influenced by quantum fluctuations. As the universe expanded and cooled, gravity began to play a significant role. Small density variations led to regions of space where matter started to clump together, forming galaxies and galaxy clusters. However, in areas where the density was lower, the gravitational pull was insufficient to attract significant amounts of matter, resulting in regions that remained largely empty. These empty spaces eventually became the voids we observe. Over time, as galaxies formed and evolved, the interactions between them contributed to the growth of these voids. The gravitational attraction between clusters and filaments of galaxies leads to an expansion of space, drawing galaxies towards denser regions and leaving the emptier areas even less populated. This effect creates a cosmic web-like structure where clusters and filaments define the boundaries of voids. Voids can occupy vast expanses, often stretching to hundreds of millions of light-years across. They serve as a critical aspect of understanding the universe's architecture. Studying these barren expanses helps astronomers analyze the interplay between dark matter, dark energy, and ordinary matter, providing insights into the universe's overall dynamics and evolution. The presence of voids exemplifies how gravity acted differently across the cosmos, shaping the architecture we observe today. The evolution of galaxy clusters is a dynamic process that unfolds over billions of years, shaped by gravitational interactions among the galaxies within them, as well as their relationships with surrounding matter and dark energy. Initially, galaxy clusters form through the merging of smaller groups of galaxies, which are themselves comprised of gas, stars, and dark matter. At first, galaxies begin to coalesce as gravity pulls them closer together. This process leads to the formation of a cluster which typically contains many galaxies, some of which may already be engaged in interactions with one another. Over time, ongoing mergers between individual galaxies occur, which can trigger bursts of star formation and change how galaxies appear. The gravitational forces within the cluster keep them bound, facilitating a complex interplay of movements and interactions. As these clusters age, they continuously acquire new members from their surroundings, drawing in nearby galaxies and material through gravitational attraction. In addition, the movement of gases within the cluster contributes to its evolution. Hot gas, known as intracluster medium, fills the space between galaxies and can emit X-rays, providing crucial information about the cluster's mass and temperature. This gas plays a significant role, as it can cool and condense, forming new stars within member galaxies, or can be heated further, influencing the overall dynamics. Over vast timescales, galaxy clusters undergo significant changes. They may experience a phenomenon called cluster merging, where two or more clusters collide, leading to complex interactions that can reshuffle their contents. As structures grow and evolve, they become more massive and may exhibit a hierarchy of formation, contributing to a larger cosmic structure. Understanding the evolution of galaxy clusters is critical, as they act as laboratories for studying the effects of dark matter, dark energy, and the fundamental laws governing cosmic evolution, helping us gain insight into the origin and fate of the universe itself. The quest to understand how common Earth-like planets are in the universe has gained significant momentum in recent years, particularly with advancements in observational technology and space missions such as the Kepler Space Telescope. Estimates suggest that Earth-like planets, which are defined by their similar size, composition and distance from their stars could be relatively common across the vast cosmos. Research indicates that potentially habitable planets are often found within what's known as the habitable zone of their stars. This is the region where conditions might allow liquid water to exist on a planet's surface, a crucial factor for life as we know it. Studies have demonstrated that many stars possess multiple planets, and a significant fraction of those can reside within this habitable zone. Some estimates propose that as many as 1 in 5 stars could host an Earth-sized planet in their habitable zone. Additionally, binaries may impact the types of planets that emerge. For instance, gas giants and icy bodies may form at different distances from the stars than they would in a solitary star system. The gravitational influence of the stars can also lead to the possibility of capturing planets that form further out or remnants of disrupted bodies, broadening the diversity of planetary types. Lastly, the orbits of planets in binary systems can be notably more complex. Some planets may possess stable orbits akin to those in a single star system, while others might have eccentric orbits or face instability due to the gravitational interplay of the two stars. This variety results in a diverse range of potential planetary systems, allowing for a broader exploration of conditions under which planets can form, a key area of inquiry for understanding the potential for life in the universe. Determining the upper size limit for a habitable planet involves assessing various factors that influence conditions necessary for life as we know it. Generally, habitable planets are those that fall within a range where liquid water can exist on their surfaces, often referred to as Earth-like planets. However, as planet size increases, several key factors come into play that may limit habitability. One primary consideration is gravity. Larger planets tend to have stronger gravitational fields, which can retain thicker atmospheres composed of various gases. While a substantial atmosphere is essential for insulating a planet and providing pressure, if the planet becomes too large, often categorized as a super-Earth, its atmosphere could also become dominated by gases like hydrogen and helium, forming a gas giant. This transition tends to limit the potential for land and liquid water on the surface, conditions that are generally required for life. Another critical aspect is the planet's geological activity. Larger terrestrial bodies are likely to have more significant internal heat, which can promote geological processes such as plate tectonics and volcanic activity. While these processes can be beneficial for creating diverse climates and ecosystems, they could also lead to extreme conditions that may be challenging for life. If a planet's size leads to excessive heating, it might create an inhospitable environment characterized by high pressures or temperatures. The balance of these factors suggests that while planets larger than Earth, up to about 2 to 3 times its size, may still maintain habitable conditions as they continue to grow in size, the likelihood of retaining Earth-like environments decreases. Consequently, the concept of a habitable zone is intricately tied to both the planet's size and its corresponding geological and atmospheric characteristics. As research progresses and we discover more exoplanets, our understanding will evolve, potentially revealing surprising limits on habitability. The potential diversity of alien biochemistries is both mind-boggling and fascinating. Life on Earth is primarily carbon-based, utilizing water as a solvent, and relies on a combination of amino acids, nucleic acids, and lipids to create its complex biological structures. However, when we venture beyond our planet, the imagination runs wild with the possibilities of life forms that might exist under entirely different conditions. For instance, scientists speculate about the potential for silicon-based life. Silicon shares many chemical properties with carbon, so it could theoretically form the backbone of complex molecules. Such life forms might inhabit environments rich in high temperatures, such as near volcanic activity, or even on certain planets and moons in our solar system that harbor extreme conditions. Beyond the molecular structure of life, the conditions required for survival could lead to a vast array of biochemical processes. For example, while Earth life thrives on oxygen to power cellular respiration, Alien organisms might use other elements like sulfur or methane in their energy-producing pathways. This could lead to life existing in places previously deemed inhospitable, such as the thick clouds of Venus or the icy surfaces of Europa and Enceladus, where subsurface oceans may harbor unseen life. Moreover, the genetic systems of extraterrestrial organisms could vary significantly from our own. They might use alternative nucleic acids instead of the familiar DNA and RNA, or utilize entirely new methods of information storage and transfer. Exploring these possibilities expands our understanding of what life could be and challenges our definitions of biology, leading us to reconsider how life might exist in myriad and unimaginable forms throughout the universe. In a methane-based ecosystem, life would evolve in environments vastly different from those we know on Earth. One prominent candidate for such ecosystems is Titan, Saturn's largest moon, where methane and ethane exist in liquid form and create vast lakes and rivers. Life forms adapting to this unique setting would likely develop biochemistries that work efficiently in frigid temperatures, as Titan's surface is around -180 degrees Celsius. Organisms in a methane-based environment might utilize methane as a primary energy source instead of oxygen. Instead of relying on photosynthesis, life could adopt chemosynthesis, creating energy through chemical reactions involving methane and hydrogen. These hypothetical organisms might develop specialized cell structures or membranes that can withstand the low temperatures and high viscosity of liquid methane, potentially resembling extremophiles found on Earth that thrive in similarly harsh conditions. The appearance and morphology of such methane-based life forms might diverge significantly from terrestrial organisms. For instance, rather than the familiar green plants, we could expect to see organisms with different pigmentation or even transparent features that help them thrive in the dim light of distant stars or the thick atmosphere of Titan. Their structures might be more robust, with rigid bodies capable of stabilizing themselves in liquid methane, potentially resembling jellyfish, or even bizarre crystalline formations that can absorb and utilize available energy sources uniquely. Furthermore, metabolism in such organisms might involve unique biochemical pathways, possibly resulting in a very different form of cellular organization. The absence of water as a solvent could mean life would not depend on amino acids in the same way we do. Instead, alternative molecules might play crucial roles in the structure and function of life, offering a glimpse into forms of biology that stretch our imagination and challenge our understanding of life's possibilities. Detecting biosignatures on distant exoplanets is one of the most exciting frontiers in modern astronomy. Scientists are focused on identifying chemical markers in the atmospheres of exoplanets that could indicate the presence of life. These biosignatures can take many forms, often involving the detection of certain gases that are typically produced by biological processes. For instance, the simultaneous presence of oxygen and methane in an atmosphere could hint at biological activity, as these gases tend to react with one another and would require a constant replenishing source, which life could provide. One of the most powerful tools at our disposal is the transit method, which involves monitoring the light from a star as a planet passes in front of it. During this transit, a small amount of starlight filters through the planet's atmosphere, allowing scientists to analyze the spectrum of light. This spectral data reveals the chemical composition of the atmosphere. By identifying specific absorption lines, researchers can determine the presence of potential biosignature gases. Additionally, future missions are planning to utilize space telescopes equipped with advanced spectrographs that can observe smaller and cooler exoplanets within their star's habitable zones. The James Webb Space Telescope, for example, is expected to greatly enhance our ability to study exoplanet atmospheres and detect potential biosignatures. These instruments will enable scientists to look for gases such as oxygen, ozone, methane, carbon dioxide, and others that, when found together, might suggest biological processes are at work. While the search for biosignatures is ongoing, it is important to remain aware of the potential for false positives. Some chemicals can also result from abiotic processes or geological phenomena. Hence, scientists must approach each finding with a careful analysis of the available evidence and consider alternative explanations. This rigorous examination will bring us closer to understanding whether life exists elsewhere in the universe and enhance our comprehension of what life beyond Earth might look like. A supernova occurs when a star undergoes a dramatic and violent explosion at the end of its life cycle. This explosive event is primarily triggered by two different processes, depending on the type of star involved. First, let us consider massive stars, those with a mass at least 8 times that of our Sun. As these stars exhaust their nuclear fuel, their cores become increasingly heavy and dense, leading to gravitational collapse. This collapse occurs when fusion reactions that normally counteract gravity can no longer sustain the core, resulting in temperatures and pressures so extreme that they ignite a series of reactions that create iron. Once iron builds up in the core, the star can no longer generate energy through fusion, causing the core to collapse under its own gravity. This collapse occurs in just a few seconds, leading to a rebound effect where the outer layers of the star are expelled outward. The shockwave from this catastrophic event creates a brilliant flash of light, releasing about 100 times more energy than the Sun will emit over its entire lifetime. This type of supernova is classified as a Type II supernova. The second leading cause of supernovae, known as a Type Ia supernova, occurs in binary systems where a white dwarf resides next to a companion star. The white dwarf can accumulate material from its partner, causing its mass to approach a critical limit called the Chandrasekhar limit. When the white dwarf surpasses this mass limit, it triggers runaway nuclear fusion in a cataclysmic explosion, resulting in the star's complete destruction. This explosion is characterized by its brightness and lacks the formation of a neutron star or black hole, as seen in the Type II scenario. Both types of supernovae have significant implications for the universe. They are responsible for dispersing heavy elements into space, contributing to the formation of new stars, planets, and ultimately, the building blocks of life. Moreover, the energy released in supernovae can influence their surrounding environments, impacting nearby star formation and possibly even the dynamics of entire galaxies. Magnetars are astonishing celestial objects that generate some of the strongest magnetic fields in the universe, often exceeding 1,000 times that of an ordinary neutron star. To understand how this occurs, it helps to consider the life cycle of massive stars. After such a star exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a dense core that collapses into a neutron star. What sets magnetars apart is the unique conditions during their formation, combined with the processes that happen later in their lives. The intense magnetic fields of magnetars arise primarily from their rapid rotation and the extreme densities within them. When the core collapses, its rotation speeds up significantly due to the conservation of angular momentum. This rapid spinning, combined with the complex motions of electrically conductive plasma within the star, generates powerful magnetic fields through a process called the dynamo effect. The motion of charged particles in the hot, dense interior of the magnetar acts like a dynamo, amplifying the magnetic field to incredible strengths. Moreover, the material in a neutron star is composed of neutrons, protons, and other particles that are densely packed into a small volume. This density leads to extreme conditions that can distort magnetic fields. As the star evolves, processes such as convective motions and magnetic field interactions can contribute further to strengthening its magnetic field. This can create a large-scale, highly organized magnetic field, distinct from what is typically observed in other celestial objects. Interestingly, magnetars can also experience magnetic outbursts, releasing enormous amounts of energy, both in the form of X-rays and gamma rays. These flares are the result of the reconfiguration of their magnetic fields, which can become unstable due to internal stresses. The combination of their intense magnetic fields and the dynamic processes occurring within them makes Magnetars one of the most intriguing and enigmatic types of stars in the cosmos, inspiring ongoing research into their mysterious behavior and extreme physics. Fast radio bursts, or FRBs, are one of the most intriguing phenomena in astrophysics, characterized by brief, intense radio pulse emissions lasting only a few milliseconds. The exact causes of these mysterious bursts remain a topic of intense investigation, but several leading theories have emerged based on observational evidence. The origins of FRBs are believed to be linked to highly energetic astronomical events. One prominent theory suggests that they may be associated with the catastrophic collapse of massive stars, which could lead to the formation of neutron stars. In particular, a specific type of neutron star known as a magnetar, identified by its incredibly strong magnetic fields, may be responsible for some FRBs. When these magnetars undergo sudden magnetic field reconfigurations or release energy from their magnetic fields, they could emit the powerful bursts of radio waves that we observe. Another possibility is that FRBs might finally be elucidated as signals from distant exotic objects such as black holes or the merger of compact objects like neutron stars. When two neutron stars collide, they create extreme conditions that may generate the rapid bursts we detect. Additionally, there are speculations about extraterrestrial civilizations potentially sending signals, although this remains a more speculative and less favored hypothesis compared to the astrophysical scenarios. Despite the progress made in understanding these bursts, the challenge lies in pinpointing their exact sources. Many FRBs are found to repeat, adding to the complexity of their nature. By studying the dispersion of the radio signals, scientists can infer the distance and environment from which these bursts originate, leading to new insights into their cosmic origins. Ongoing research and advances in technology are helping to unlock the mysteries surrounding fast radio bursts, offering tantalizing glimpses into extreme astrophysical processes at play in the universe. Star formation in extreme environments like the centers of galaxies presents a fascinating challenge due to the intense conditions present in these regions. The core of a galaxy, especially in those with active supermassive black holes, is characterized by high radiation levels, gravitational forces, and significant turbulence. Despite these extreme factors, stars still manage to form, albeit through different mechanisms than in quieter regions of space. In galactic centers, one crucial aspect of star formation is the presence of massive amounts of gas and dust, which gather in dense molecular clouds. These clouds are often subjected to turbulent conditions created by the gravitational pull of the supermassive black hole and the energetic activity surrounding it. Interestingly, while the intense environment could disrupt star formation, it also leads to the compression of gas, which plays a vital role in the process. As the gas clouds become denser, they can undergo gravitational collapse, eventually forming new stars. The presence of high-energy radiation from accreting matter around supermassive black holes can lead to heating and ionization within these dense clouds. Yet, certain regions of the clouds can shield themselves from this radiation. This allows parts of the molecular clouds to maintain their cool temperatures, enabling the process of star formation to continue. Additionally, interactions between gas clouds can trigger shock waves, further compressing the material and sparking the formation of new stars. In such extreme environments, star formation may occur more rapidly, leading to the creation of massive stars. These stars evolve quickly and can end their lives in spectacular supernova explosions, which then enrich surrounding regions with heavier elements, promoting further star formation. This cyclic process contributes to the dynamic evolution of the galaxy over time, illustrating how even in the most hostile conditions, the universe has a remarkable ability to create and nurture new stars. Ultra-high energy cosmic rays are among the most mysterious and energetic particles in the universe, with energies exceeding 1 billion giga-electron-volts, which is significantly higher than any produced in human-made particle accelerators. Understanding their origin has puzzled scientists for decades, leading to various theories regarding their sources, which are primarily linked to some of the most energetic astrophysical phenomena known. One leading candidate for the origin of ultra-high-energy cosmic rays is supernova remnants. When massive stars explode, they release tremendous amounts of energy, creating shock waves that can accelerate particles to extraordinarily high energies. These shock waves interact with surrounding gas and magnetic fields, providing the necessary conditions for particles, primarily protons, to gain energy and escape the remnants of the explosion. While this process is a viable source, it may not account for all the highest energy cosmic rays detected. Another strong contender is active galactic nuclei, particularly those associated with supermassive black holes at the centers of galaxies. As matter spirals into these black holes, it releases immense amounts of energy in the form of jets, which can accelerate particles to ultra-high energies. The conditions surrounding these massive black holes, including their powerful magnetic fields and turbulent environments, serve as ideal environments for cosmic ray acceleration. Gamma-ray bursts, which are extremely energetic explosions associated with the collapse of massive stars and mergers of compact objects, have also been proposed as potential sources. The immense energy released during these events can accelerate particles to incredibly high energies. However, determining the exact mechanisms and locations of particle acceleration in these extreme environments remains a significant area of research. Despite advances in observational techniques, the precise origins of ultra-high-energy cosmic rays remain elusive. Ongoing studies utilizing observatories around the world aim to establish connections between detected cosmic rays and their potential sources, helping to unveil the intricacies of these energetic particles and improve our understanding of the universe's most powerful phenomena. Binary star systems consist of two stars orbiting around a common center of mass, and the exchange of mass between these stars is a fascinating process that can significantly influence their evolution. Mass transfer occurs when one star evolves and exhausts its nuclear fuel, often expanding into a larger, more volatile state, such as a red giant. This expansion can lead to various outcomes, depending on the specific characteristics of the binary system. As one star in the binary system expands, its outer layers may spill over into the gravitational pull of its companion star. This process is often facilitated by the presence of an accretion disk, which forms around the receiving star as it pulls in material from its neighbor. The accretion disk acts as a funnel, allowing material to spiral down onto the surface of the companion star. The efficiency of this mass transfer depends on factors such as the distance between the stars and the rate at which the donor star expands. There are different regimes of mass transfer, with the two primary types being stable and unstable mass transfer. In stable mass transfer, the process occurs slowly and steadily, allowing the receiving star to adjust gradually to the increased mass, often leading to long-term changes in brightness and composition. In contrast, unstable mass transfer can lead to rapid and dramatic exchanges, resulting in significant effects such as nova eruptions, where the accreted material undergoes explosive thermonuclear reactions on the surface of the receiving star. Mass transfer can drastically alter the evolution of both stars in a binary system. For instance, the gaining star might undergo changes that lead to the formation of a white dwarf or even a neutron star or black hole, depending on the amount of mass it receives and its original mass. This complex interplay of mass exchange ultimately shapes the life cycles of stars and can lead to spectacular cosmic events like Type Ia supernovae, providing essential insights into stellar evolution and the dynamics of binary star systems. In the core of a red supergiant star, a dramatic series of processes unfolds just before the star collapses. After exhausting its nuclear fuel for fusion reactions, the red supergiant has progressed through multiple stages in which it burns increasingly heavier elements. Initially, hydrogen is fused into helium, then helium into carbon and oxygen, and this continues until iron accumulates in the core. As the core builds up iron, an essential transformation occurs. Iron is unique in that fusing it does not produce energy. Instead, it consumes energy. This results in a halt in the star's ability to generate the outward pressure needed to counteract the immense gravitational forces pulling the core inward. Without that pressure, the balance that has sustained the star for millions of years begins to deteriorate, leading to further instability. With the core unable to support itself, the gravitational forces cause it to collapse rapidly. This collapse occurs at remarkable speeds, leading to an increase in density and temperature. As the core becomes denser, conditions can rise to extremely high temperatures of around several billion degrees. This creates a situation where photodisintegration occurs, as energetic photons can break apart iron nuclei, generating a variety of lighter particles such as protons and neutrons within the core. The final moments are marked by a build-up of energy from the core's collapse and the subsequent rebound effect from the outer layers of the star. Once the core collapses to a critical point, which is typically around 3 solar masses, it will transform into a neutron star or possibly a black hole, depending on the mass. This crash culminates in a supernova explosion, unleashing extraordinary amounts of energy and ejecting the outer layers of the star into space. This magnificent event not only marks the end of the red supergiant, but also plays a crucial role in the cosmic recycling of elements, enriching the interstellar medium and paving the way for future star formation. Reconciling quantum mechanics with general relativity is one of the most profound challenges in modern theoretical physics. These two pillars of our understanding of the universe operate very successfully within their own domains, but are fundamentally incompatible when attempting to apply them simultaneously in extreme environments, such as near black holes or during the moments after the Big Bang. Quantum mechanics describes the behavior of particles at very small scales, where probabilities and uncertainties play key roles. On the other hand, general relativity, formulated by Albert Einstein, describes the gravitational force as the curvature of spacetime caused by mass and energy, operating on a much larger scale. When scientists try to apply quantum principles to gravitational fields, several fundamental issues arise, particularly related to the concept of spacetime itself, which general relativity treats as a smooth continuum, whereas quantum mechanics suggests a discrete nature at the Planck scale. One approach to reconciling these theories is through the development of a quantum theory of gravity. This is still an active area of research, with several theoretical frameworks being explored. One prominent candidate is string theory, which posits that fundamental particles are not point-like objects, but rather tiny vibrating strings. String theory suggests that these strings exist in higher dimensions, thereby providing a structure that could unify all fundamental forces, including gravity, within a single theoretical framework. Another approach is loop quantum gravity, which seeks to quantize spacetime itself. This theory proposes that spacetime is made up of discrete units, like a fabric woven from loops. By applying quantum principles to the geometry of spacetime, loop quantum gravity aims to create a coherent picture that includes both quantum effects and gravitational interactions. While promising, each of these theories still faces significant challenges, including testing their predictions through experiments and observations. Scientists continue to explore ways to bridge the two realms, focusing on understanding phenomena like black hole evaporation, the early universe, and potential observational consequences. Although a complete reconciliation remains elusive, ongoing efforts highlight the quest to deepen our understanding of the universe at its most fundamental levels. Quantum entanglement is one of the most intriguing phenomena in quantum mechanics, reflecting a deep connection between particles that often defies our classical understanding of the universe. When two or more particles become entangled, their quantum states become linked in such a way that the state of one particle cannot be fully described without considering the state of the other, no matter how far apart they are. This relationship persists even when the entangled particles are separated by vast distances, a feature that Albert Einstein famously referred to as spooky action at a distance. The true nature of entanglement lies in the principles of superposition and non-locality. When particles are entangled, they exist in a state of superposition, where each particle is not in a definite state, but rather in multiple potential states simultaneously. Upon measurement of one particle, its state collapses to a definite value, and this instantaneously determines the state of the other particle. This instantaneous correlation raises profound questions about the nature of information and causality in quantum mechanics. Entanglement challenges our understanding of reality, prompting discussions about whether classical intuitions about separability and locality hold true in the quantum realm. Experimental tests of Bell's theorem have shown that entangled particles exhibit correlations stronger than that allowed by classical physics, confirming that nature operates according to quantum rules that are fundamentally different from those we experience in everyday life. The implications of quantum entanglement extend beyond theoretical physics. They have practical applications in emerging fields like quantum computing and quantum cryptography. By harnessing entangled states, researchers are developing technologies that exploit these unique properties for unprecedented computational power and secure communication techniques. Ultimately, while quantum entanglement continues to puzzle and inspire scientists, it stands as a testament to the complexity and interconnectedness of the universe at the quantum level, inviting further exploration into the fundamental nature of reality itself. The question of whether space-time is quantized at the smallest scales is a central topic in theoretical physics, particularly in the quest to unify quantum mechanics and general relativity. Current understanding suggests that space-time, as described by general relativity, is a smooth continuum. However, when considering phenomena at extremely small scales, on the order of the Planck length, which is about 1.6 times 10 to the minus 35 meters, traditional descriptions of space-time may break down. Several theoretical frameworks propose that spacetime might indeed be quantized. Loop quantum gravity is one such approach, which suggests that spacetime itself consists of discrete units, resembling a network made up of tiny loops. In this theory, the geometric properties of spacetime are quantized, meaning that space and time could be represented as a collection of finite, indivisible elements. This model aims to reconcile the smooth geometry of general relativity with the discrete nature of quantum mechanics. String theory is another candidate that posits a fundamental description of matter and forces not in terms of point particles, but as one-dimensional strings vibrating at specific frequencies. These strings exist in higher dimensions, and the compactification of these dimensions could lead to a quantized structure of spacetime. In string theory, the interactions and dynamics of strings could imply that spacetime has a fundamental granular quality at very small scales. Despite these theories, the quantization of spacetime is not yet established and remains a topic of active research. No experimental evidence currently confirms the discrete nature of spacetime, primarily because the scales involved are well beyond the reach of current technology. As scientists continue to explore the intersections of gravity and quantum mechanics, the question of whether spacetime is fundamentally quantized may progressively yield insights, contributing to a deeper understanding of the universe's structure at its most fundamental levels. The universe as we understand it has three dimensions of space: length, width, and height, along with the dimension of time, forming what is commonly known as spacetime. In this framework, events are described by four-dimensional coordinates, where three dimensions account for spatial positions and the fourth dimension represents the progression of time. This four-dimensional model aligns well with both general relativity and our everyday experiences. However, many theoretical physicists propose that our universe may actually possess additional dimensions beyond the familiar four. String theory, for instance, suggests that fundamental particles are not point-like objects but rather one-dimensional strings that vibrate in multiple dimensions. In its most popular formulations, string theory requires 10 or even 11 dimensions to be mathematically consistent. These extra dimensions are theorized to be compactified or curled up at such small scales that they remain undetectable in our everyday observations. The idea of extra dimensions provides intriguing possibilities for unifying the fundamental forces of nature. It allows for various mechanisms that could explain the gravitational force's relative weakness compared to other fundamental forces, as well as offering potential insights into the nature of dark matter and dark energy. However, direct evidence for these additional dimensions remains elusive. While some experiments, such as those conducted at particle colliders like the Large Hadron Collider, aim to probe high-energy phenomena that could hint at extra dimensions, the confirmation of their existence is still an open question. As research continues and our understanding of the fundamental structure of the universe evolves, the true nature of dimensions beyond the observable 3 spatial and 1 temporal may eventually become clearer, enriching our comprehension of reality itself. Quantum decoherence is a phenomenon that describes the process by which a quantum system loses its quantum coherence, transitioning from a state of superposition to a classical mixture of states. This occurs when a quantum system interacts with its environment, leading to the emergence of classical properties that we observe in macroscopic objects. Understanding decoherence is crucial because it helps explain how classical reality arises from the quantum realm. The process of decoherence begins when a quantum system, initially in a superposition of states, interacts with external environmental factors, such as particles, fields, or even photons. As the system becomes entangled with its environment, the information about the various states encoded in the superposition gets dispersed into the surrounding environment. This interaction effectively measures the quantum system, wherein the coherent states start to lose their phase relationships due to the coupling with the environment. One of the key aspects of decoherence is the environment's influence on the quantum system's possible states. As the system interacts with numerous environmental factors, the coherent superposition gradually transforms into an incoherent mixture of states, causing the original quantum properties to diminish. The crucial element here is that the environmental interactions tend to be random and uncontrollable, making it impossible to recover the initial quantum coherence. Decoherence helps to bridge the gap between quantum mechanics and classical physics by explaining why macroscopic objects behave classically despite being composed of quantum entities. It serves as a mechanism that accounts for the classical world's determinism and locality, while also revealing the inherent probabilistic nature of quantum systems. The study of decoherence not only sheds light on fundamental questions about the nature of reality, but also has important implications in fields like quantum computing and quantum information, where managing coherence is essential for developing stable quantum systems. Every measurement we take holds an element of uncertainty, and this uncertainty is rooted in various factors, including the tools we use and the inherent nature of what we are measuring. The concept of limits in precision is closely associated with 2 fundamental principles of physics: the limitations imposed by quantum mechanics and the effects of noise in measurement systems. As we aim for more precise measurements, we confront phenomena such as the Heisenberg uncertainty principle. This principle dictates that we cannot simultaneously know certain pairs of properties, like the position and momentum of a particle, with absolute precision. Consequently, this limitation sets a fundamental boundary on how accurately we can measure certain quantum systems, affecting our overall precision in scientific measurements. Moreover, the technology used to facilitate measurements also introduces constraints. Instruments like telescopes and particle accelerators have their own limits, often defined by noise, calibration errors, or physical degradation over time. As we strive for finer details, we may find that the resolution of our instruments becomes a significant factor in determining our measurement limits. Our quest for precision continues to push the boundaries of science and technology. Scientists develop innovative methods such as quantum sensors, which leverage the principles of quantum mechanics to enhance measurement precision. Yet even with advancements, it remains crucial to acknowledge that the journey toward perfect precision is fraught with both theoretical and practical limitations, inherently shaping our understanding of the universe. The emergence of gravity from quantum effects is a complex and still largely unresolved topic in theoretical physics. At its core, scientists are exploring the relationship between general relativity, which describes gravity as the curvature of space-time caused by mass, and quantum mechanics, which governs the behavior of subatomic particles. The challenge lies in reconciling these two pillars of modern physics into a coherent framework. One intriguing approach is the idea of quantum gravity, which suggests that spacetime itself might have a granular structure at the smallest scales, much like matter is composed of atoms. In this view, spacetime could be made up of discrete units or quanta, hinting that gravity could emerge from the interactions at this fundamental level. Researchers propose that this quantum nature of spacetime may lead to gravity manifesting as a collective effect from these microstates, similar to how temperature emerges from the motion of countless particles. Another line of thought explores concepts such as loop quantum gravity and string theory. Loop quantum gravity posits that the fabric of spacetime is woven from loops of quantum fields, where gravity is a result of the way these loops interact. String theory, on the other hand, suggests that fundamental particles are not point-like, but rather tiny strings vibrating in multiple dimensions. In this framework, gravity emerges naturally as one of the force-carrying particles, known as the graviton, arising from the configurations and interactions of these fundamental strings. Ultimately, while the idea of gravity emerging from quantum effects presents a fascinating frontier in physics, the lack of experimental evidence and theoretical consensus highlights the complexity of these theories. As researchers continue to probe the depths of quantum mechanics and the nature of spacetime, they inch closer to unveiling a more complete understanding of how gravity fits into the quantum landscape of the universe. The ultimate fate of the universe is a captivating question that has intrigued scientists for many years. Current observations and theories suggest that the universe's future could lead towards several scenarios, primarily the Big Freeze or the Big Crunch, but there may be other possibilities as well. Understanding these outcomes involves analyzing the expansion of the universe and its underlying forces. The Big Freeze, also known as heat death, emerges as a likely outcome based on the current observations of cosmic expansion. The universe is observed to be expanding at an accelerating rate, driven by a mysterious force known as dark energy. If this acceleration continues indefinitely, galaxies will drift further apart, stars will exhaust their nuclear fuel, and space will cool as energy spreads out. Over extremely long timescales, this cold, dark, and empty universe would be the ultimate fate, characterized by a lack of thermodynamic activity. On the other hand, the Big Crunch posits a different fate, where the expansion of the universe eventually halts and reverses, leading to a contraction. If the density of matter in the universe was sufficiently high, gravitational forces could overcome the expansion, causing the universe to collapse back in on itself. This scenario would end with all matter and energy spiraling into a singularity, potentially leading to a new Big Bang or a complete halt to the universe's existence. However, current evidence suggests that the density of the universe is not enough to trigger such a collapse. Beyond these two dominant theories, other possibilities do exist, such as the Big Rip, where the expansion of the universe accelerates to the point that it tears apart galaxies, stars, and even atomic structures. The fate of the universe remains a central question in cosmology, heavily contingent upon ongoing observations and the nature of dark energy. The answers to these profound inquiries continue to evolve, capturing the imaginations of scientists and stargazers alike. The concept of phase transitions is well understood in the realm of condensed matter physics, where substances like water can change between solid, liquid, and gas states depending on temperature and pressure. Transferring this idea to the universe suggests that it could also experience dramatic changes in its state under certain conditions, leading physicists to explore the possibility of cosmic phase transitions. Theoretical models propose that early in the universe's history, it underwent various phase transitions during key moments, such as during the first few moments after the Big Bang. One such example is the transition from a quark-gluon plasma to hadronic matter, leading to the formation of protons and neutrons as the universe cooled. Similarly, as the universe expanded and cooled further, phase transitions might have contributed to the formation of various structures like galaxies and cosmic filaments. The Doom. In more contemporary discussions, scientists consider the implications of a phase transition related to the mysterious phenomenon of dark energy. If the energy density associated with dark energy were to change significantly, such a transition might lead to a state where the universe's expansion shifts dramatically, possibly resulting in scenarios like the previously mentioned Big Rip, or even other unknown fates for the cosmos. Research into this concept remains speculative, as understanding the detailed behavior of dark energy continues to challenge our current knowledge. These potential phase transitions reflect the dynamic nature of the universe, suggesting that it is not a static entity, but rather one that could change in profound ways in response to varying conditions. The exploration of such transitions combines aspects of both cosmology and high-energy physics, leading to exciting inquiries about the formation of the universe and its potential futures. As scientists probe deeper into these mysteries, they endeavor to uncover the underlying principles governing the cosmos and its ever-evolving phases. The formation of a bubble of true vacuum in our universe is a fascinating and somewhat alarming scenario proposed by physicists. In theoretical physics, the concept of a true vacuum refers to a state with the lowest possible energy, contrasting with our current vacuum, which is filled with quantum fields and exhibits various forms of energy, including dark energy. If such a bubble were to emerge within our universe, the consequences could be decidedly dramatic. As it stands, a true vacuum bubble represents a phase transition where different physical laws or constants might apply. If a bubble of true vacuum were to form, it would expand at the speed of light, relentlessly consuming the surrounding space, including all matter and energy in its path. This expansion would create a region where the familiar laws of physics as we know them would no longer hold. The fabric of reality could fundamentally change, leading to an entirely different universe inside the bubble, while the region it had consumed would cease to exist. The impact of a true vacuum bubble would likely be catastrophic for any structures or life forms within its vicinity. As the bubble expanded, it would annihilate everything it encountered, transforming complex atomic arrangements into a state of true vacuum. If the bubble were to encounter Earth, the planet would be obliterated almost instantaneously without any time for escape or preparation. Although this scenario might sound like science fiction, it arises from legitimate theoretical frameworks in high-energy physics. The idea remains a topic of discussion and speculation among scientists, primarily because no evidence supports the existence of such a true vacuum bubble in our universe. However, it provides a compelling lens through which to explore the nature of our universe, the properties of vacuum states, and the potential for dramatic phenomena existing within the fabric of reality itself. The stelliferous era, the current epoch in the timeline of the universe, is defined by the brightness and activity of stars. This era is characterized by the formation, evolution, and eventual death of stars, making it a vibrant period in cosmic history. Scientists estimate that the stelliferous era will last for around 10 trillion years before transitioning into a much quieter phase known as the degenerate era. Distribution of elements will change, enriching the interstellar medium with heavier elements produced in stars, which are vital for the formation of planets and life. As the stelliferous era progresses and stars exhaust their nuclear fuel, they will eventually exhaust the available hydrogen necessary for fusion. The late stelliferous era will witness the decline of star formation as galaxies deplete their gas reserves. During this time, existing stars will evolve into red giants, white dwarfs, neutron stars, or black holes, depending on their initial mass. Eventually, the number of new stars producing light will diminish greatly, leading to a more subdued universe. Following the stelliferous era, the universe will transition into the degenerate era, characterized by the remnants of stars and the cooling of any remaining stellar objects. This will be a time marked by dark, inert remnants floating through space for a period of trillions of years, eventually giving way to a universe predominantly filled with black holes and subatomic particles. The journey from one era to the next encapsulates not only the life cycles of stars, but also the dramatic evolution of the cosmos across unimaginable timescales. After the last black hole evaporates, the universe will enter a profoundly different state, often referred to as the black hole era, followed by the dark era. Through the process known as Hawking radiation, black holes slowly lose mass and energy, leading to their eventual evaporation over incredibly long timescales, potentially on the order of trillions of years or more. As black holes evaporate, they release energy in the form of radiation, incrementally increasing the overall temperature of the surrounding space. However, this process is exceptionally slow, particularly for massive black holes. Once the last black hole has evaporated, the cosmological landscape will change dramatically. The remnants of black holes will vanish, leaving behind a universe devoid of significant cosmic structures such as stars and galaxies. In this dark era that follows, the universe will enter a state of extreme desolation and coldness, as the earlier stellar bodies have exhausted their nuclear fuel and the remnants of black holes have disappeared. Only low-energy particles will remain scattered throughout the vast emptiness. With no new sources of light or heat, the universe will settle into a state that is uniformly cold, with a temperature approaching absolute zero. During this time, entropy will continue to increase, leading to a nearly static and barren cosmos. All matter will eventually decay into lighter particles over immense timescales due to processes such as proton decay, hypothesized in various grand unified theories. The universe in this far-distant future will be a dark and sparse expanse, no longer vibrant with the activities of stars or galaxies, but rather a fading echo of a once dynamic and energetic cosmos. This scenario raises profound questions about the very nature of existence and time itself. The end of black holes encapsulates a journey toward a universe where all potential for cosmic activity has diminished, leaving behind a hauntingly quiet and lifeless space. This speculation about the far future deepens our understanding of the universe's fate and the laws of physics governing its endless evolution. The idea of a cyclical universe is a compelling concept that has captured the imaginations of scientists and philosophers alike. This notion suggests that instead of a linear progression from a singular beginning to an eventual end, the universe could undergo repeated cycles of expansion and contraction. These cycles could involve phases of big bangs, followed by phases of big crunches or other transformative states. One prominent model of a cyclical universe is known as the ekpyrotic universe, which posits that our universe could arise from the collision of two higher dimensional objects, or branes, in a multi-dimensional space. Such collisions could trigger a Big Bang, leading to the expansion of our universe. Following a period of expansion, the universe could eventually stop expanding and start contracting, culminating in another collision or bounce that leads to a new expansion phase. This framework suggests an eternal series of cosmic cycles, each giving rise to a universe similar yet distinct from the last. Another approach to the cyclical concept comes from the idea of quantum gravity, where physicists explore how the laws of quantum mechanics might allow for universe-bouncing scenarios. In some models, the universe experiences a singularity that precedes the Big Bang, allowing for a contraction phase that transitions smoothly into a new expansion phase without an absolute beginning or end. While the cyclical universe presents a fascinating alternative to current cosmological models, several challenges and unanswered questions persist. The dynamics of cosmic expansion, the behavior of dark energy, and the implications of thermodynamics over multiple cycles all need careful examination. Additionally, the nature of entropy plays a crucial role in these discussions, as the second law of thermodynamics implies that disorder should ultimately increase. In a strictly cyclical model, mechanisms to reset or manage entropy would need to be proposed. Exploring the possibility of a cyclical universe not only invites speculation about the past and future, but also challenges our understanding of fundamental concepts like time, existence, and the ultimate fate of cosmic evolution. As research continues, the quest to understand whether our universe is part of an endless cycle remains a pivotal question at the frontier of theoretical physics. The concept of parallel universes, often referred to as the multiverse, has emerged as a fascinating area of inquiry in modern cosmology and theoretical physics. While the idea may sound like science fiction, several interpretations of quantum mechanics and cosmological theories suggest different forms of parallel universes might actually exist. One prominent framework supporting the existence of parallel universes is based on the many worlds interpretation of quantum mechanics. According to this interpretation, every time a quantum event occurs with multiple possible outcomes, the universe splits into branches. Each outcome unfolds in its own separate universe, leading to an infinite number of parallel realities coexisting simultaneously. This means that every decision or random event could create diverging paths, resulting in a vast tapestry of realities that encompass all possibilities. Another theoretical framework arises from inflationary cosmology. During the rapid expansion that followed the Big Bang, small fluctuations could create regions of space with different physical properties, resulting in bubble universes. Each bubble could have distinct laws of physics or constants, forming a multiverse of varied realities. This model suggests that our observable universe might be just one of many bubbles, each developing independently. Additionally, some theories in string theory propose extra dimensions beyond our familiar three-dimensional space. These extra dimensions might allow for different configurations of fundamental forces and particles, leading to diverse regions that could be interpreted as distinct universes. While the notion of parallel universes is alluring, it's essential to note that direct evidence for their existence remains elusive. Many scientists view the multiverse as a speculative idea, prompting both enthusiasm and skepticism within the scientific community. As research advances and our understanding of quantum mechanics, cosmology, and the nature of reality deepens, the quest to determine whether parallel universes exist continues to provoke profound questions about the very nature of existence itself. The interaction between different universes, if they exist, is an intriguing concept that raises profound questions about the nature of reality and the fundamental forces that govern the cosmos. While numerous theories suggest the potential for multiple universes, understanding how they might interact involves complex and speculative ideas, often drawing upon principles from quantum mechanics, general relativity, and advanced theories such as string theory. One perspective on possible interactions comes from the framework of the multiverse, particularly in the context of the many worlds interpretation of quantum mechanics. In this view, different branches of reality created by quantum events do not directly influence each other. Instead, they exist independently, each representing a separate outcome. This means that while they coexist in a sort of vast multiverse, interactions as we normally understand them don't occur across these branches. Any communication or influence would be fundamentally impossible based on this interpretation. Another scenario involves the concept of bubble universes arising from inflationary cosmology. In this model, our universe may be one of many disconnected regions that have formed during a rapid expansion phase in the early universe. If these bubble universes exist in a higher dimensional space, it is conceivable that they could interact under certain conditions. This could lead to gravitational effects, such as the merging or collision of bubbles, affecting the physical properties or structures of the universes involved. Such interactions might yield detectable phenomena in our universe, although direct evidence remains speculative. String theory introduces additional complexity through the idea of extra dimensions. In this framework, universes could be represented as branes, multidimensional objects that can interact with one another within a higher dimensional space. If two branes were to collide, this interaction could potentially lead to the creation of new physical phenomena or even trigger new universes. The dynamics of these brane interactions could also influence the fundamental constants and laws of physics in the universes involved. Despite these fascinating possibilities, discussions of interuniversal interactions remain largely theoretical. Currently, there is no empirical evidence for the existence of parallel universes, let alone frameworks that demonstrate how such universes would interact. Nevertheless, exploring these questions stimulates philosophical and scientific debates about the nature of reality, coexistence, and the complexity of existence in an expansive multiverse. As research progresses, the inquisitiveness surrounding the interactions of potential universes continues to challenge our understanding of the cosmos. The question of whether we could ever detect evidence of other universes is a captivating topic within cosmology and theoretical physics. While the notion of multiple universes, or the multiverse, is intriguing, the challenges in gathering definitive evidence for their existence remain substantial. Several theoretical approaches suggest possible pathways toward detecting these elusive realms. One potential avenue lies within the cosmic microwave background radiation, the afterglow of the Big Bang. Some physicists propose that collisions between bubble universes or interactions between different cosmic regions could leave imprints or anomalies in this radiation. If our universe is one of many, there may be detectable signatures resulting from such interactions, potentially observable as irregularities in the temperature fluctuations of the cosmic microwave background. While some studies have attempted to identify these anomalies, conclusive evidence remains absent. Another avenue involves gravitational waves, which are ripples in spacetime caused by cataclysmic cosmic events. Certain multiverse models suggest that significant events, such as the merging of bubble universes or collisions between cosmic structures, could generate gravitational waves with unique signatures. Future upgrades to gravitational wave detectors might allow scientists to observe signals indicative of such extraordinary cosmic events, providing compelling indirect evidence for other universes. Quantum mechanical phenomena also open a window of possibilities. For example, experiments that explore quantum entanglement might yield insights into whether multiple universes influence one another, even subtly. If scientists could detect discrepancies or effects that cannot be explained by our current understanding of quantum mechanics, it might suggest that interactions with other universes are at play. Despite these intriguing concepts, direct evidence of other universes remains elusive and is inherently difficult to obtain due to the nature of our observational limits. Current scientific methodologies rely heavily on testing hypotheses and models through experimental evidence within our own universe. Thus far, the multiverse remains a speculative framework, prompting exciting discussions while also requiring caution in drawing conclusions. As science advances, researchers continue to pursue viable avenues for exploring the multiverse idea, expanding the boundaries of our understanding about the cosmos and our place within it. The idea of multiverses encompasses a variety of theoretical frameworks, each proposing different types of universes that could exist alongside our own. While definitions and categorizations can vary, scientists typically describe several broad types of multiverses based on their origins and underlying mechanisms. One prominent model is the inflationary multiverse, which arises from the theory of cosmic inflation. This scenario posits that during the rapid expansion shortly after the Big Bang, different regions of space could stop inflating at different times, creating bubbles or pockets of space that evolve into distinct universes, each with its own physical properties. The inflationary multiverse suggests a vast number of such bubble universes, potentially leading to infinite variations in parameters like the strength of fundamental forces, the number of dimensions, or the types of particles. Another noteworthy category is the many worlds interpretation of quantum mechanics. In this view, every time a quantum event occurs with multiple possible outcomes, the universe branches into different realities, each reflecting one of the possible results. This interpretation leads to an immense and possibly infinite number of parallel universes, all of which coexist but do not interact with one another. Each branch represents a different outcome based on quantum decisions, from routine choices to microscopic phenomena. Furthermore, there are theories emerging from string theory, suggesting that the fundamental nature of particles is rooted in higher dimensions. In some configurations, these additional dimensions allow for various distinct vacua or states of energy, each leading to different universe characteristics. The string theory multiverse could involve a vast landscape of possibilities where different combinations of physical parameters lead to distinct universes governed by unique laws of physics. Finally, the anthropic multiverse presents another perspective, where the conditions of our universe are explained by the existence of many universes with varying properties. In this view, our universe is just one of many, and the specific conditions that allow for life are statistically rare. This anthropic principle posits that we can only observe a universe fine-tuned for life because we exist within it, among countless other uninhabitable options. While these frameworks offer compelling models for understanding the concept of multiverses, direct empirical evidence remains elusive. As research in theoretical physics advances, the exploration of different types of multiverses continues to challenge our understanding of reality, inviting questions about the fundamental nature of existence itself and our place within the cosmos. The laws of physics in other universes could differ significantly from those in our own, depending on the conditions and parameters that govern each distinct universe. As various theories of the multiverse propose, the fundamental constants and the nature of physical laws might not be universal, but rather could vary dramatically across different realms. In the inflationary multiverse, for example, bubble universes may each have their own set of physical constants, such as the gravitational constant or the speed of light. These variations could lead to vastly different behaviors of matter and energy, resulting in alternative forms of chemistry, stellar formation, or even gravitational interactions. Consequently, a universe with differing laws of physics might support entirely different types of matter or life, or it could be inhospitable to the existence of structures like galaxies and stars as we know them. The many worlds interpretation of quantum mechanics suggests that every possible outcome of a quantum event exists in separate branches of reality. In this framework, while some physical laws may remain consistent across all these worlds, the specific outcomes and events could lead to universes behaving in unique ways. For instance, in one universe, particular interactions could yield entirely different states of matter, while in another, the processes governing time and causality may take on new forms. String theory, with its emphasis on extra dimensions and different vacuum states, also implies that universal constants could change based on the configuration of these dimensions. By influencing the fundamental forces, like electromagnetism or nuclear forces, these variations could create environments where certain physical phenomena behave unpredictably compared to our universe. The nature of gravity, for example, might differ significantly, possibly altering the way galaxies form or how black holes evolve. Interestingly, some theorists have hypothesized about universes where the laws of physics are so distinct that they might not support traditional notions of time or causality. In such universes, the conceptual framework of physics as we understand it might not even apply, presenting realities that could seem incomprehensible to beings from our universe. While the exploration of laws of physics in other universes remains largely theoretical and speculative, these ideas lead to profound questions about the nature of reality. They challenge our understanding of fundamental principles and invite us to consider a much more diverse and complex cosmos, one in which the rules governing existence could vary widely across the multiverse. Strange matter is a theoretical form of matter that arises from the study of quarks, which are the fundamental constituents of protons and neutrons. It's hypothesized to consist of up, down, and strange quarks, the latter being heavier varieties of quarks. This intriguing concept emerges primarily in the context of high-energy physics and astrophysics, especially concerning the behavior of neutron stars and the conditions prevalent in particle collisions. Currently, strange matter has not been conclusively observed in nature. Still, theoretical models suggest that it could exist under extreme conditions, such as those found in the core of neutron stars. Neutron stars are incredibly dense remnants of supernova explosions, where gravity compresses matter to such an extent that protons and electrons merge to form neutrons. It's theorized that in the highest densities, this neutron-rich environment could lead to the formation of strange matter, where strange quarks begin to appear alongside the more familiar up and down quarks. One of the most significant implications of strange matter involves its potential stability compared to ordinary nuclear matter. If strange matter is stable, it could theoretically lead to structures called strange stars, which would be entirely composed of strange quarks. These hypothetical stars might possess different properties than conventional neutron stars, exhibiting unique behavior in terms of mass, size, and stability. Interestingly, discussions surrounding strange matter also touch on the concept of strangelets, hypothetical small lumps of strange matter that could exist independently. If strangelets exist and come into contact with regular matter, there are concerns that they might convert ordinary matter into strange matter, leading to catastrophic consequences, though this remains purely speculative. While strange matter is a fascinating topic in theoretical physics, more research is necessary to explore its potential existence and properties. Experiments at particle accelerators, such as the Large Hadron Collider, continue to probe the fundamental properties of quarks, providing a better understanding of how matter behaves under extreme conditions. As science advances, the quest to uncover the nature of strange matter could yield insights into the universe's most enigmatic phenomena and the fundamental composition of matter itself. Quark-gluon plasma is a state of matter that is believed to have existed just moments after the Big Bang, before the universe cooled enough for quarks and gluons to combine and form protons and neutrons. This extreme state is characterized by several interesting and unique properties that distinguish it from the ordinary matter we encounter in everyday life. One significant property of quark-gluon plasma is that it exhibits extreme temperatures and densities, often exceeding millions of degrees Celsius. Under such conditions, quarks and gluons, which are typically confined within hadrons such as protons and neutrons, become liberated from their usual structures. In this state, the quarks and gluons are free to move independently, creating a highly energetic and fluid-like medium. When cooled sufficiently, quarks and gluons can recombine, transitioning back into ordinary hadronic matter, which gives scientists a glimpse into the conditions that existed in the early universe. The behavior of quark-gluon plasma also exhibits a remarkable aspect known as confinement. As energy density decreases, the strong force, the fundamental interaction that binds quarks together, becomes increasingly powerful, ultimately forcing quarks to remain confined within hadrons. At temperatures exceeding a critical threshold, quarks lose their restrictions and the plasma state occurs, making it a rare moment when quarks can roam freely instead of being locked inside particles. Another fascinating property of quark-gluon plasma is its strong coupling, which leads to unexpected behaviors. At thermal equilibrium, quark-gluon plasma behaves like a nearly perfect fluid, demonstrating very low viscosity, meaning it can flow with minimal resistance. This property suggests that even in such extreme conditions, the strong interactions among particles lead to collective behaviors similar to those seen in ordinary fluids. This nearly perfect fluidity has been observed in heavy ion collision experiments at facilities like the Large Hadron Collider and the relativistic Heavy Ion Collider. Lastly, the study of quark-gluon plasma provides valuable insights into the fundamental forces that govern the universe. By examining the properties and behaviors of this exotic state of matter, scientists can explore the strong force and the conditions that dominated the universe's earliest moments. As researchers continue to investigate quark-gluon plasma through particle collisions, they hope to unlock mysteries about the very fabric of matter and the evolution of the cosmos itself. Exotic matter captivates the curiosity of scientists due to its unique properties, such as negative mass or negative energy density. These characteristics set it apart from the ordinary matter we encounter in daily life. Theoretical physics suggests that conditions allowing for stable configurations of such matter could very well exist, potentially hiding in the far reaches of the cosmos or emerging under extreme conditions that have not yet been replicated on Earth. Current scientific understanding proposes numerous theories that utilize exotic matter, particularly regarding concepts like wormholes or warp drives. These fascinating ideas depend heavily on the presence of exotic matter to work as envisioned. For example, the notion of a stable wormhole requires exotic matter to stabilize its throat, preventing it from collapsing under gravitational forces. If stable configurations of exotic matter truly exist, they could represent a key to unlocking travel across the universe or even a gateway between different dimensions. The challenge lies not in believing that such configurations might exist, but in our ability to detect and study them. Simply put, the universe is immense and complex, filled with phenomena we have yet to explore fully. Advanced technologies and methods in particle physics, astronomy, and cosmology may eventually uncover signs of exotic matter, reshaping our understanding of physics and the fabric of reality itself. While theoretical physicists continue to explore the implications of exotic matter, the potential for its existence encourages a broader inquiry into the nature of the cosmos. Each discovery in this field brings us closer to understanding the fundamental forces and unusual forms that make up our universe, reminding us that the quest for knowledge often leads to the most unexpected revelations. At extremely high pressures, matter undergoes profound transformations that challenge our understanding of its behavior. Under such conditions, the forces that bind atoms and molecules together are subjected to immense stress. As pressure increases, materials can become denser as atoms are forced closer together, leading to various states of matter that deviate significantly from our everyday experiences. One fascinating outcome of extreme pressure is the alteration of atomic structures. For example, things that normally exist as gases can become liquids or solids. In the case of elements like carbon, high pressure can convert graphite, the soft form of carbon, into diamond, an exceptionally hard structure. This phenomenon occurs as the atoms rearrange themselves into a more compact configuration, stabilized by the high pressure. Furthermore, matter can exhibit entirely new states, such as metallic hydrogen. Under pressures found deep within gas giant planets like Jupiter, hydrogen transitions into a metallic state, which is hypothesized to conduct electricity with incredible efficiency. This not only alters the properties of the materials, but also can affect the magnetic fields and energy dynamics of celestial bodies. As scientists explore the effects of high pressure in laboratories and through astrophysical observations, they broaden our understanding of matter itself. These findings suggest that similar processes may occur throughout the universe, providing insights into the birth and evolution of stars, planets, and even the characteristics of exotic phenomena like neutron stars, where matter is compressed to densities surpassing those of atomic nuclei. Neutron stars represent some of the densest objects in the universe, formed from the remnants of supernova explosions. Within their cores, conditions are so extreme that the known laws of physics are pushed to their limits. As a result, the interior of a neutron star is believed to harbor exotic and potentially undiscovered states of matter, a concept that excites astrophysicists and theorists alike. Let's say, at the core of a neutron star, the pressure exceeds a staggering amount, leading to intense gravitational forces that compress matter far beyond what we encounter on Earth. In such environments, neutrons, which are typically stable particles, become primary constituents of matter. However, as pressure continues to increase beyond typical neutron densities, matter could transition into various states that we have yet to observe or understand. These could include quark-gluon plasma, a state where quarks and gluons, the fundamental building blocks of protons and neutrons, exist freely rather than being confined within particles. Furthermore, theorists propose the existence of bizarre phases, such as hyperons or meson condensed states, which may arise under extreme conditions. Hyperons are particles that contain strange quarks, and their presence could fundamentally alter the properties of neutron star matter. These exotic states might also influence the structure, stability, and lifespan of neutron stars, leading them to exhibit different behaviors than those predicted by conventional models. Exploring these undetected states of matter is not just a theoretical exercise. It holds significant implications for our understanding of the universe. Observations of neutron stars through gravitational waves and electromagnetic signals provide vital clues, offering insights into their inner workings. As research progresses, the potential for discovering new states of matter at the core of neutron stars serves as a thrilling frontier in modern physics and cosmology, hinting at phenomena that challenge our current notions of matter itself. Cosmic inflation refers to a hypothesis that proposes a rapid expansion of the universe during the first few moments after the Big Bang. This theory emerged from the need to explain several puzzling observations about the universe, such as its large-scale homogeneity, isotropy, and the uniformity of the cosmic microwave background radiation. While the precise cause of cosmic inflation remains a matter of research and debate, various compelling theories have been put forth by scientists. One primary idea posits that inflation was driven by a specific field known as the inflaton field. This hypothetical field would have been responsible for the enormous energy fluctuations that initiated the rapid expansion. At this early stage, particles and energy were densely packed together, creating a state of extremely high energy density. As the inflaton field evolved, it produced a repulsive force, causing the universe to expand exponentially in a fraction of a second. This expansion smoothed out any irregularities and allowed for the formation of a homogeneous universe. Another approach involves the concept of phase transitions within the universe's fabric. Just as water changes states when heated, the universe may have experienced a phase transition that released energy, causing the inflationary expansion. Some researchers propose that this might have occurred as the universe cooled, transitioning from a high-energy state to one of lower energy density, influencing the dynamics of the universe's growth. Despite the theories proposed, a consensus on the specifics of what initiated cosmic inflation remains elusive. Researchers gather evidence through observations of the cosmic microwave background radiation, which carries the imprint of the inflationary period, and through studies of the universe's large-scale structure. As technology and theoretical models advance, the quest to understand the origins and mechanics of cosmic inflation continues to be an exciting and vital part of modern cosmology, offering insights into the very nature of the universe itself. Cosmic inflation, which describes the rapid expansion of the universe in the moments immediately following the Big Bang, eventually came to an end due to the dynamics of the inflaton field. While this field initially drove the exponential expansion, its energy underwent a transformation that triggered the cessation of inflation. Understanding how this process unfolded helps clarify the transition from the inflationary period to what is known as the standard cosmological evolution. As inflation progressed, the inflaton field gradually cooled and evolved. The energy density associated with this field did not remain constant. Instead, it diminished over time. Once the inflaton field reached a critical energy threshold, it underwent a phase transition. This transition saw a portion of the field's potential energy convert into matter and radiation, leading to the phenomenon known as reheating. This moment was pivotal, as it injected energy into the universe in the form of particles, laying the groundwork for the subsequent periods of cosmic evolution. The moment inflation ended was marked by the establishment of a spatially homogeneous and isotropic universe filled with matter and radiation. Following this transition, the universe shifted from being a flat, rapidly inflating space to one where gravitational effects began to dominate the dynamics. The end of inflation led to a universe that expanded at a decelerated rate, allowing for the formation of structures such as galaxies and clusters of galaxies over billions of years. The specific details of why inflation stopped remain an active area of research, as various models propose different mechanisms for the inflaton field's dynamics. Some models suggest additional interactions or fields that could influence the end of inflation. As observations of the universe continue to improve, scientists hope to glean more information about the nature of the inflaton field and the conditions that prompted inflation to cease, ultimately gaining a deeper understanding of the universe's formative moments. The idea of cosmic inflation restarting in our universe is a fascinating area of theoretical inquiry in cosmology. While inflation, as we understand it, was a brief period of rapid expansion that occurred right after the Big Bang, some scientists have speculated about the possibilities of inflationary dynamics re-emerging in certain contexts. However, the likelihood and mechanisms for such a scenario involve complex and speculative ideas. One of the intriguing concepts is the notion of eternal inflation, which suggests that inflation could persist in some regions of the universe, even as other regions evolve into the more familiar cosmological states we observe today. In this model, quantum fluctuations could trigger localized patches of inflation that continue indefinitely, potentially leading to a multiverse where different regions experience different inflationary histories. In such a framework, while our observable universe appears homogeneous and isotropic, it may exist within a larger inflating cosmos. For inflation to restart in a localized manner within our current universe, certain conditions must be favorable. These include the presence of the inflaton field or a similar field that can produce enough energy density to drive an inflationary phase. However, such conditions would require significant alterations in the dynamics of the energy fields governing our universe, a scenario that remains speculative and largely in the realm of theoretical physics. Furthermore, the implications of a restarted inflationary phase would be profound. If inflation were to resume in a particular region, it could lead to the formation of new universes or pockets of space, potentially separating from our own observable reality. This raises intriguing questions about the nature of our universe, the stability of existing structures, and the future evolution of cosmic expansion. In conclusion, while the prospect of cosmic inflation restarting presents an exciting line of inquiry, it remains a topic of theoretical exploration rather than an established scientific consensus. Understanding the conditions and mechanisms that would allow for such an event requires further research and observation, continuing to provoke curiosity about the fundamental nature of our universe. Quantum fluctuations during the inflationary period of the universe played a crucial role in shaping the large-scale structure we observe today. These fluctuations are minute variations in energy that arise from the principles of quantum mechanics. In the context of cosmic inflation, they occurred on incredibly small scales and represented random changes in the density of matter and energy in the rapidly expanding universe. As inflation progressed, the universe expanded exponentially. During this rapid expansion, tiny quantum fluctuations were stretched beyond their original scales, effectively frozen into the fabric of space-time. These small density variations became more pronounced, seeding the formation of large-scale structures. The regions with slightly higher density would experience stronger gravitational pull, attracting more matter over time. Conversely, the regions with lower density would face less gravitational attraction, leading to a vacuum of matter. When inflation ended, the energy contained in these fluctuations converted into matter and radiation during the reheating phase. As the universe cooled, these slight differences in density led to a gravitational collapse of matter in the areas of higher density. This process eventually resulted in the formation of galaxies, clusters, and superclusters, creating the vast and intricate web of cosmic structures observed in the universe today. Essentially, these quantum fluctuations acted as the initial seeds around which everything we see today has formed. Without inflation, fluctuations would not have been stretched sufficiently into the size where their impact could persist after the universe began cooling. The interplay between quantum mechanics and large-scale cosmic dynamics is a testament to the deep connections between the microcosm of subatomic particles and the macrocosm of cosmic structures, illustrating how fundamental processes govern the evolution of the universe on all scales. The concept of regions of space still undergoing inflation is linked to the theory of eternal inflation, which posits that while our observable universe experienced a defined period of rapid expansion, inflation may continue in isolated regions outside of our observable reach. This model suggests that the universe consists of a vast multiverse, where different regions can experience inflation at different times, creating a patchwork of universes that vary in their physical properties. In eternal inflation scenarios, quantum fluctuations can trigger localized pockets of inflation that persist even as inflation ceases in adjacent areas. These pockets continue to expand exponentially, while the surrounding regions evolve into more conventional cosmological states. This means that while we observe a uniform and isotropic universe, there could be other regions, potentially infinite in number, that remain in an inflationary state. The implications of this are profound. If such regions exist, new universes could form through a process known as bubbles of inflation. In this model, each bubble would represent a unique universe with its own distinct physical laws and conditions. The idea that regions of inflation persist introduces a compelling possibility of a multiverse where various realities coexist, each evolving according to its own set of rules. Although these concepts are fertile ground for theoretical exploration, they currently lack direct observational evidence. The challenge lies in the fact that these inflationary regions would be entirely disconnected from our observable universe, limiting our ability to detect or study them directly. Nevertheless, ongoing research in cosmology and advancements in observational techniques may help distinguish the boundaries of our universe and provide insights into the nature of inflation and the potential for an inflating multiverse. The study of these concepts remains an exciting frontier, raising questions about the fundamental nature of reality itself. Time, as we experience it, flows in a single direction, typically referred to as the arrow of time, and this directionality is observed at all scales, from the microscopic realm of particles to the cosmic scale of galaxies. The predominant factor contributing to this phenomenon is the second law of thermodynamics, which states that entropy, or the measure of disorder in a system, tends to increase over time. This gives rise to a natural tendency for systems to evolve from states of lower entropy to higher entropy, effectively creating a forward-moving arrow of time that aligns with our everyday experiences. In the microscopic world of physics, processes such as particle interactions often appear to be time-symmetric, meaning the fundamental laws governing these particles do not inherently favor a direction of time. However, when we consider the collective behavior of large numbers of particles, this time symmetry breaks down due to statistical mechanics. As systems evolve, we observe an increase in disorder, which aligns with our perception of time flowing forward. At larger scales, in cosmology, this arrow of time remains consistent. The expansion of the universe, observed through redshift in distant galaxies, suggests a singular evolution of time as the universe continues to expand and get cooler. The universe itself is transitioning from a hot, dense state to a cooler, more dispersed one, further emphasizing the irreversible nature of time's passage on a cosmic scale. Interestingly, while the flow of time is typically perceived as linear and unidirectional, there are theories within quantum mechanics and general relativity that challenge this perception under specific conditions. Concepts like time dilation in relativistic physics or quantum entanglement hint at the complexity of time and its flow, suggesting there could be scenarios where our intuitive understanding of time might not hold. Nevertheless, in the macroscopic world and the overall universe, the flow of time remains a consistent, forward-moving phenomenon linked deeply to the fundamental laws of thermodynamics and the evolution of systems. The notion of causality, which asserts that a cause precedes its effect, is a foundational principle in physics. However, at the quantum level, the behavior of particles and fields introduces intriguing scenarios that challenge our classical understanding of causality. Quantum mechanics operates on principles that can seem counterintuitive, leading to interpretations where traditional cause and effect relationships may appear to be violated. One of the phenomena that sparks discussions about causality is quantum entanglement. When two particles become entangled, the state of one particle is instantly correlated with the state of another, regardless of the distance separating them. If one particle is measured, the outcome appears to instantaneously influence the other particle's state. This behavior, often summarized by the phrase "spooky action at a distance," has led to debates about whether such instantaneous correlations imply a violation of causal order. However, it's crucial to understand that while entanglement exhibits non-local correlations, it does not allow for faster-than-light communication or the transmission of information, preserving the essence of causality. The changes in one particle do not influence the other in a manner that could convey usable information, which means causality, as we understand it, remains intact even in the quantum realm. Another fascinating aspect involves certain interpretations of quantum mechanics, such as those related to time travel or closed time-like curves. These theoretical propositions suggest scenarios where the usual sequence of cause and effect might be reversed or bypassed. While these ideas provoke thoughtful exploration of the nature of time and reality, they remain speculative and have not been empirically validated. While quantum mechanics presents phenomena that challenge classical notions of causality, the fundamental principle that causes precede effects remains largely preserved in practical terms. The exploration of quantum causality continues to be a rich field of theoretical inquiry, revealing deeper insights into the nature of reality and the underpinnings of the universe, but has yet to produce concrete examples that definitively violate causality as we understand it. Near the singularity of a black hole, the behavior of time undergoes dramatic changes as predicted by general relativity. A black hole singularity is the core region where density becomes infinitely large and the gravitational forces are intense, effectively curving space-time to such an extent that our conventional understanding of time and space breaks down. As one approaches this enigmatic point, time behaves in ways that can seem counterintuitive compared to our everyday experiences. For an observer falling into a black hole, time would appear to flow normally at first. However, as they approach the event horizon, the boundary surrounding the black hole beyond which no information or matter can escape, the effects of gravitational time dilation become profound. According to relativity, time passes more slowly in stronger gravitational fields. Therefore, to an outside observer watching someone falling into a black hole, the person would appear to slow down and never actually cross the event horizon, effectively freezing in time as the light they emit gets increasingly redshifted. From the perspective of the falling observer, they would cross the event horizon without noticing any immediate change, but as they get closer to the singularity, they would encounter extreme tidal forces that could lead to spaghettification, where objects are stretched and compressed. At the singularity itself, conventional laws of physics cease to be applicable, and time as we understand it may lose its meaning entirely. Some theories suggest that time might be rendered irrelevant at that point, as the equations of general relativity do not provide a clear understanding of the nature of time in such extreme conditions. This breakdown of the conventional flow of time near a black hole's singularity raises profound questions about the nature of time itself and the limits of our current understanding of physics. While general relativity provides a framework for examining these phenomena, a more complete theory that unifies general relativity with quantum mechanics may be required to fully grasp the behavior of time at and around singularities. The study of black holes remains one of the most intriguing areas of modern physics, with each discovery offering potential insights into the fabric of time and space itself. The question of whether time is fundamental or emergent is one of the most profound and debated topics in modern physics and philosophy. The distinction between fundamental and emergent concepts pertains to whether time is a basic building block of the universe, or if it arises from more fundamental processes and structures that do not inherently involve time. If time is considered fundamental, it means that time is woven into the very fabric of the universe. In classical physics, time is treated as an absolute dimension in which events occur and sequences are ordered. This perspective aligns with traditional views found in Newtonian mechanics, where time is a fixed backdrop against which all physical processes unfold. In this view, time flows consistently regardless of the state of matter or energy. On the other hand, the emergent view posits that time could arise from more fundamental elements, such as quantum processes or the interactions of particles. Some theorists argue that time might emerge from thermodynamic processes, notably through the increase of entropy as described by the second law of thermodynamics. In this framework, the flow of time is a result of statistical behavior in large systems rather than a primitive entity on its own. So, in a universe devoid of complex interactions, there may be no distinct notion of time. Emergent time concepts also find roots in approaches to quantum gravity, where space and time might not be part of the fundamental description of the universe. In some string theory, models, or loop quantum gravity, time may emerge from more primitive, timeless states. In these scenarios, the relationships between particles and the physical dynamics govern the perception of time. As our understanding of the universe deepens through ongoing research and experimentation, the nature of time as fundamental or emergent continues to be explored. Both perspectives stimulate significant philosophical discourse and challenge our understanding of reality. Unraveling the true nature of time could lead to groundbreaking insights about the universe, its laws, and our place within it. The concept of time behaving differently in various regions of the universe arises from the understanding of general relativity and the effects of gravity on the flow of time. According to this theory, time is not uniform across the universe. Rather, it can be influenced by gravitational fields and relative velocities. In this context, regions of the universe can indeed exhibit variations in the passage of time. One prominent example of this effect is gravitational time dilation. As an object approaches a massive body, such as a planet or a black hole, the gravitational field increases, causing time to move more slowly for that object compared to an observer positioned farther away from the massive body. This phenomenon has been confirmed through experiments involving precise atomic clocks placed at different altitudes. Clocks closer to Earth's surface, where gravity is stronger, tick slightly slower than those at higher altitudes. Another aspect involves the effects of rapid movement or high velocities as described by the theory of special relativity. When an object approaches a significant fraction of the speed of light, time for that object slows down relative to a stationary observer. This means that if one were to travel through space at relativistic speeds, they would experience a different passage of time compared to those remaining on Earth. Moreover, theoretical models, such as those involving wormholes or cosmic strings, propose that there could be regions of space where the usual understanding of time might break down altogether or become considerably altered. In such constructs, the topology of space-time could allow for unusual interactions with time, potentially enabling scenarios like time travel or creating areas where time behaves in fundamentally different ways. While these discussions rely heavily on theoretical frameworks, they point to the fascinating reality that time is deeply interconnected with the fabric of space and the forces at work within the universe. As our understanding of physics expands, particularly in the realms of quantum gravity or cosmology, the possibility of regions where time behaves differently remains an exciting frontier for exploration and discovery. Each breakthrough in this field might illuminate new aspects of how time interacts with the universe as a whole. Supermassive black holes, which can contain millions to billions of times the mass of our Sun, play a pivotal role in the evolution of galaxies. These colossal objects are typically found at the centers of most large galaxies, including our own Milky Way. Their influence extends far beyond their immediate vicinity, impacting various aspects of galactic structure and dynamics. One significant way supermassive black holes affect galactic evolution is through gravitational interactions. As they exert intense gravitational forces, they can influence the motion of stars and gas within the galaxy, affecting the overall stability and structure. This gravitational pull can lead to phenomena such as the formation of dense stellar bulges and the arrangement of stars in specific patterns around the galactic center. Additionally, supermassive black holes are associated with energetic processes during events such as accretion. As matter falls into the black hole, it forms an accretion disk, heating up and emitting radiation across different wavelengths, including X-rays and radio waves. This energetic activity can effectively regulate star formation within the galaxy. When accretion rates are high, the resulting energetic outflows can heat surrounding gas and expel it from the galaxy, creating feedback that suppresses further star formation. This feedback loop can prevent the galaxy from accumulating excessive amounts of gas into stars, thus shaping the galaxy's evolutionary path. Furthermore, supermassive black holes can facilitate the merging of galaxies. During such mergers, the gravitational influence of the black holes can lead to the efficient transfer of gas toward the centers of the newly formed galaxies. This can trigger bursts of star formation and can also lead to the growth of the black hole itself. Over time, the interplay between merging galaxies and their supermassive black holes contributes to the larger-scale evolution of galactic structures across the universe. Overall, supermassive black holes act as integral engines of galactic evolution, influencing star formation, the dynamics of galaxy structure, and the interaction of galaxies during mergers. Ongoing research in observational astronomy continues to shed light on their profound impact, revealing connections between the growth of supermassive black holes and the evolution of the galaxies that host them. These findings enhance our understanding of the universe's complex tapestry and the processes that shape it. The cessation of star formation in some galaxies is a significant aspect of galactic evolution, and several interconnected processes contribute to this phenomenon. One of the primary factors is the depletion of gas, the essential raw material for star formation. When galaxies exhaust their reservoir of cold gas, which can happen due to extensive star formation or outflows driven by supernovae and overall stellar activity, they lose the ability to form new stars. Once the gas supply diminishes considerably, the galaxy transitions into a quiescent or passive state, significantly reducing its star formation rate. Another important factor is the effect of supermassive black holes located at the centers of galaxies. When these black holes actively consume gas and matter, they can create powerful jets and outflows that inject energy into the surrounding interstellar medium. This energetic feedback can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. Additionally, the gravitational interactions that occur during galaxy mergers can also induce strong star formation initially, but can lead to the expulsion of gas or the heating of the gas in the aftermath, stifling future star formation. Environmental effects also play a critical role in determining a galaxy's star-forming capabilities. Galaxies that reside in dense environments such as galaxy clusters often experience processes like ram pressure stripping, where the hot intracluster medium strips away the surrounding gas from the galaxy as it moves through. This removal of gas can quickly suppress star formation. Additionally, gravitational interactions with neighboring galaxies can lead to tidal forces that disrupt the gas reservoirs necessary for star formation. Over cosmic time, these factors contribute to a diverse range of galaxy types observed today, from actively forming starburst galaxies to quiescent elliptical galaxies with little to no ongoing star formation. Understanding the mechanisms that halt star formation helps astronomers piece together the intricate tapestry of galaxy evolution and the broader processes that govern the life cycle of galaxies in the universe. Each discovery in this domain enhances our grasp of the dynamic interrelationships between galaxies, their environments, and the universe as a whole. Galaxies are not isolated entities. They actively interact with the surrounding intergalactic medium in a process that allows them to exchange matter. This exchange occurs primarily through several mechanisms, including the phenomenon of galactic winds, gas accretion, and galactic mergers. Galactic winds are powerful outflows of gas driven by stellar winds and supernova explosions within a galaxy. When massive stars end their lives in explosive supernova events, they release enormous amounts of energy and materials into space. This process can propel gas and dust out of the galaxy and into the intergalactic medium, enriching it with heavy elements synthesized in stars. Some of this ejected material can later be reaccreted by other galaxies, contributing to their growth and evolution. On the other hand, galaxies can also gain matter from the intergalactic medium. Through a process called gas accretion, they draw in primordial hydrogen and helium, which constitutes the majority of matter in the universe. This inflow of gas can fuel star formation, helping galaxies to grow and evolve over time. This exchange is vital for the life cycle of galaxies, as it allows them to replenish the materials lost to stellar processes and maintain their ability to form new stars. Galactic mergers further complicate this dynamic relationship. When two galaxies collide, their interstellar gas clouds merge, resulting in a surge of star formation known as a starburst. During this process, gas from both galaxies can flow into the intergalactic medium as they interact gravitationally, and their structures become disrupted. Such events not only facilitate the exchange of matter, but also significantly influence the properties of the merging galaxies, ultimately shaping their evolution for billions of years. Starbursts in galaxies are intense periods of star formation that can significantly alter a galaxy's structure and composition. These bursts of activity are typically triggered by a variety of events, with gravitational interactions being one of the most prominent factors. When galaxies collide or come close to one another, their gravitational forces can compress gas and dust within each galaxy. This compression triggers a surge in star formation, leading to a rapid increase in the number of stars being born over a relatively short time period. Another significant trigger for starbursts can be the interaction of a galaxy with its environment. For instance, in dense regions of the universe like galaxy clusters, galaxies can experience a phenomenon known as ram pressure stripping. This occurs when the intergalactic medium exerts pressure on a galaxy's gas. If this external pressure is strong enough, it can strip away the galaxy's outer gas layers, causing the remaining gas to become more concentrated. This concentrated gas can then collapse to form new stars at an accelerated rate. Additionally, internal processes play a crucial role in initiating starbursts. The formation of new stars can be fueled by the accumulation of gas that is channeled into the galaxy's central regions. A possible mechanism behind this accumulation is the feedback from existing stars and supernovae, which can heat and redistribute the surrounding gas, making it more susceptible to collapse and formation into new stars. This self-regulating process can lead to an explosive increase in star formation when conditions align just right. Starbursts can also occur in response to major events in a galaxy's life cycle, such as the infall of gas from the intergalactic medium or the aftermath of a merger with another galaxy. These processes inject fresh gas into the galaxy, sparking renewed star formation. However, unlike regular star formation, which can continue at a steady pace, starbursts are characterized by their short, explosive duration, during which a significant fraction of the galaxy's gas is converted into stars, fundamentally shaping its future evolution. Galactic magnetic fields are fascinating phenomena that arise from a combination of processes, primarily involving the movement of electrically charged particles and the dynamics within a galaxy. These magnetic fields are thought to originate from the motions of ionized gases and the rotation of galaxies, which can generate and sustain magnetic fields over vast cosmic timescales. At the core of magnetic field formation is the dynamo effect, which occurs when a conducting fluid, such as the ionized gas found in galaxies, moves through a magnetic field. As stars and gas within a galaxy rotate and interact, their motion creates turbulence and vortices that induce electric currents. These electric currents, in turn, generate magnetic fields. Initially, these fields may be relatively weak and disorganized, but as the fluid continues to move and interact, the magnetic fields become amplified and structured, leading to the magnetic fields we observe in galaxies. As galaxies evolve, their magnetic fields also undergo significant changes. For instance, the radial and spiral structures of magnetic fields are often shaped by the galaxy's rotation and the flow of gas within it. Interactions such as mergers with other galaxies can also distort and amplify magnetic fields, creating intricate patterns. The merger can squeeze interstellar gas and amplify existing fields, resulting in more complex configurations that can affect star formation rates and the overall dynamics of the galaxy. Over time, galactic magnetic fields can evolve further due to various processes such as cosmic ray generation and the influence of supernova explosions. When massive stars explode, they not only release energy but also inject magnetic fields back into the interstellar medium. This magnetic material interacts with existing fields, contributing to their growth and structural complexity. The continuous interplay between magnetic field formation, star dynamics, and cosmic events ensures that galactic magnetic fields remain an active area of study in modern astrophysics, revealing ongoing insights into the nature of galaxies themselves. The diverse morphologies of galaxies, ranging from spiral and elliptical to irregular shapes, are shaped by a variety of factors, including their formation histories, interactions with other galaxies, and the dynamics of their constituent stars and gas. The initial conditions during a galaxy's formation play a crucial role in determining its structure. For example, galaxies that formed from more uniform gas can develop a more spiral design, creating well-defined arms filled with young stars and nebulae, whereas those with more chaotic initial conditions may evolve into elliptical shapes, characterized by their smooth, featureless profiles. Interactions and mergers between galaxies significantly influence their morphologies as well. When two galaxies collide, their gravitational forces can distort their shapes and trigger intense bursts of star formation. This merging process can result in a range of outcomes, including the formation of irregular galaxies that lack a defined structure or the transformation of spiral galaxies into elliptical ones. Such interactions can also redistribute stars and gas within a galaxy, leading to a complex internal structure that reflects the violent history of its formation. The environment in which a galaxy resides also plays a pivotal role in its morphology. In denser regions of the universe, such as galaxy clusters, gravitational interactions are more frequent, leading to a higher rate of mergers and transformations. In such environments, galaxies can lose their gas through processes like ram pressure stripping, which inhibits their ability to form new stars and can lead to the transformation of their structure. Conversely, in less dense environments, galaxies may retain more of their gas, preserving their spiral shapes and promoting ongoing star formation. Finally, the role of dark matter cannot be overlooked. The gravitational influence of dark matter, which makes up a significant portion of the universe's mass, contributes to the stability and structure of galaxies. The distribution and properties of dark matter halos around galaxies affect their dynamical evolution, impact star formation processes, and ultimately influence how galaxies maintain or change their morphologies over time. The intricate interplay of these factors creates a rich tapestry of galaxy shapes and structures across the cosmos. The Great Attractor is a massive gravitational anomaly located in the direction of the Centaurus and Hydra constellations, roughly 200 million light-years away from Earth. It represents a region of space with a significant concentration of mass, believed to be influencing the motion of galaxies within our local supercluster, known as the Laniakea supercluster. This mysterious force draws galaxies towards itself, leading to noticeable peculiar motions that deviate from the overall expansion of the universe. At the heart of the Great Attractor lies a large cluster of galaxies, with a particularly massive component called the Norma cluster. However, what makes the Great Attractor particularly intriguing is not only its gravitational pull but also the difficulty astronomers face in observing it directly. The region is partially obscured by the Milky Way's galactic plane, making it challenging to study the exact contents and structure of this gravitational powerhouse. The gravitational effects of the Great Attractor extend over a vast area, affecting the motion of numerous galaxies, including the Milky Way. These influences cause galaxies within the vicinity to experience a collective motion towards this region of space, contributing to the phenomenon known as the flow of galaxies. Observations have shown that our local group of galaxies, along with others, is moving towards the Great Attractor at substantial velocities. Research into the Great Attractor continues to reveal important insights into the large-scale structure of the universe. It serves as a reminder that the cosmos is full of complex gravitational interactions, where unseen masses can significantly influence the motion of visible matter. This phenomenon, capturing the gravitational dance of countless galaxies, highlights the interconnectedness of cosmic structures as they navigate through the ever-expanding universe. The cold spot in the cosmic microwave background radiation is an intriguing feature that has captured the attention of scientists since its discovery. This cold spot represents an area in the remnant radiation from the Big Bang that exhibits a temperature significantly lower than that of the surrounding regions. The cosmic microwave background, or CMB, serves as a snapshot of the early universe, providing a wealth of information about its origins, structure, and subsequent evolution. One leading explanation for the cold spot is related to fluctuations in the density of matter in the early universe. As the universe expanded after the Big Bang, small quantum fluctuations led to variations in density, resulting in the formation of clusters and voids. The cold spot may correspond to a large cosmic void, an underdense region where fewer galaxies and less matter reside. This void, being less populated, would emit less radiation, leading to a cooler temperature in that specific area of the cosmic microwave background. Another hypothesis suggests that the cold spot might be the result of an interaction with a massive superstructure, such as a galaxy cluster. As light from the cosmic microwave background travels through the universe, it can be influenced by massive objects due to gravitational lensing, which distorts the path of light. If the cold spot resulted from such lensing effects, it could indicate the presence of significant mass, altering the perceived temperature of the radiation. Some researchers have even proposed more exotic explanations, such as the possibility of evidence for new physics beyond the standard cosmological model. Although these ideas are still under investigation, they inspire scientists to delve deeper into understanding the cold spot and its implications for the overall structure of the universe. Ultimately, the existence of this cold spot enriches our comprehension of cosmic history, prompting ongoing inquiry into the fundamental properties of the cosmos itself. The alignment of quasar polarizations over vast distances is a captivating phenomenon that raises intriguing questions about the nature of cosmic structures and the behavior of light in the universe. Quasars, or quasi-stellar objects, are highly luminous active galactic nuclei powered by supermassive black holes. As radiation emitted by these black holes travels through intergalactic space, it can exhibit polarization, a property that describes the orientation of light waves. Several factors contribute to the observed alignment of quasar polarizations. One key aspect is the influence of the surrounding intergalactic medium, which can contain magnetic fields that affect the propagation of light. As light from quasars passes through these magnetic fields, any interactions can induce polarization, aligning the light wave's orientation in specific directions. If the magnetic fields are coherent over large scales, they can lead to a consistent alignment of quasar polarizations across considerable distances. Another significant factor involves the gravitational lensing effects caused by massive foreground objects, such as galaxy clusters between the quasar and Earth. When light from a quasar is bent around these massive bodies, the resulting paths taken by the light can cause polarization patterns that reflect this gravitational influence. This lensing can reinforce the alignment of polarization angles, especially if multiple quasars are affected by a similar gravitational field. Additionally, intrinsic properties of the quasars themselves can play a role in this alignment. Some quasars have structures such as jets, which are outflows of relativistic particles emitted along the rotational axis of the black hole. The emission from these jets can be inherently polarized, and if multiple quasars exhibit similar orientations of their jets, this could contribute to the observed alignments of their polarizations when viewed from Earth. The alignment of quasar polarizations invites further exploration into the underlying mechanisms and the large-scale structures of the universe. By analyzing these patterns, scientists can glean insights into the cosmic web, the behavior of light, and the interplay between matter and radiation over vast cosmic distances. The appearance of some galaxies as being older than the universe itself stems from several complex factors related to cosmic evolution, observational techniques, and the methods used to estimate a galaxy's age. One of the most significant contributors is the phenomenon of redshift, which provides insights into the distance and consequently the age of galaxies. When we observe light from distant galaxies, we often find that it is redshifted due to the expansion of the universe. This means that the light we observe from those galaxies was emitted in the past. In certain instances, astronomers identify galaxies whose light has taken a substantial amount of time to reach us. If a galaxy is observed at a high redshift, it can appear to be older because we are looking at it as it was when the universe was much younger. However, because electromagnetic radiation takes time to travel, this can create the illusion that some galaxies formed quickly after the Big Bang and have remained relatively unchanged, which can lead to estimates of their ages exceeding the age of the universe. Additionally, the techniques used to determine the ages of galaxies may contribute to the confusing results. Astronomers often use the properties of stars within these galaxies, such as their stellar populations and the presence of older, evolved stars, to estimate ages. If a galaxy has a significant population of older stars, it may be classified as older than expected. However, these estimates can vary based on the models used and the assumptions regarding star formation rates and stellar evolution, which can lead to discrepancies in age estimates. Another possible explanation involves the existence of fossil galaxies, which are thought to have formed very early in the history of the universe. These galaxies could have undergone rapid star formation and evolved quickly before the universe was fully structured. As a result, their characteristics might suggest ages that appear to exceed the overall age of the universe. Understanding these complex relationships and discrepancies is essential for refining our models of galaxy formation and evolution, as well as for reconciling observations with our current cosmological framework. As more data is collected and analyzed, scientists continue to gain deeper insights into the age and nature of galaxies, deepening our understanding of the universe's history. The Fermi paradox poses a puzzling question. Given the vast number of stars and potentially habitable planets in the universe, why have we not yet encountered any signs of extraterrestrial life? Named after the physicist Enrico Fermi, This paradox highlights an apparent contradiction between high estimates of the probability of extraterrestrial civilizations and the lack of evidence or contact with such civilizations. One possible explanation for the Fermi paradox lies in the sheer scale and age of the universe. With billions of galaxies, each containing millions to billions of stars, many planets may exist that could potentially support life. However, the distances between these stars and planets are immense. The vastness of space combined with the finite speed of light means that even if intelligent civilizations exist nearby, the time it takes for their signals to reach us makes contact extremely unlikely within a human lifetime. Another factor is related to the development and sustainability of intelligent life itself. It is possible that while simple life forms may be common in the universe, the emergence of complex, intelligent civilizations could be exceptionally rare. This could be due to a myriad of reasons, including the specific conditions required for life to evolve, extinction events that can wipe out developing civilizations, or technological and societal challenges that prevent sustained long-term existence. Civilizations might self-destruct through warfare, ecological collapse, or technological disasters before they can develop the means to communicate with us or explore beyond their solar systems. Additionally, the behavior of advanced civilizations may also play a role. If intelligent life does exist, they might adopt policies of isolation or deliberately choose not to communicate with other civilizations. They could be using technologies we cannot detect, or they may simply lack the inclination to explore or interact with less advanced life forms. Some theorists suggest that we may be in a great filter scenario, where civilizations face significant challenges that limit their ability to reach a stage where they can communicate or expand beyond their own star systems. Ultimately, the Fermi paradox fosters ongoing discussions in astrobiology and cosmology. It raises fundamental questions about life's development, technological evolution, and our place in the universe. As researchers continue to explore the cosmos with more advanced telescopes and missions, the search for extraterrestrial life remains one of humanity's most compelling quests, potentially redefining our understanding of intelligence and the nature of life itself. The observed shortage of lithium-7 in the universe is a fascinating aspect of cosmology and nucleosynthesis. The Big Bang theory predicts that a variety of light elements, including hydrogen, helium, and lithium, were created during the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. However, observations of the actual abundance of lithium-7 in the universe reveal that it is significantly lower than theoretical predictions. Several factors contribute to the lithium-7 discrepancy. One prominent explanation involves the processes that occurred during the formation and evolution of stars. When stars form, they primarily consume hydrogen and helium, and through nuclear fusion they can alter the abundances of light elements. In particular, stars can destroy lithium during nuclear fusion processes. As stars evolve and undergo stellar nucleosynthesis, any lithium present can be depleted, especially in higher mass stars that burn fuel quickly and reach hotter temperatures. Additionally, the nature of stellar outflows and winds plays a role. When stars shed mass, they can expel freshly synthesized material into the interstellar medium. However, the process often results in a net loss of lithium-7, as this element can be photodissociated or transformed into other elements in the high-energy environments found in stellar interiors or during supernova explosions. Another aspect influencing lithium-7 abundance is the cosmic ray spallation process. Cosmic rays, high-energy particles traveling through space, can collide with heavier elements, resulting in nuclear reactions that produce lighter elements, including lithium. However, this process may not produce enough lithium-7 to account for its lower observed abundance. Lastly, the initial conditions of the universe are also a consideration. The assumptions made about the density of baryonic matter and the expansion rate of the universe can change the predicted abundances for light elements like lithium-7. Variations in these conditions during the Big Bang stage may lead to a lower lithium-7 yield than expected. The lithium-7 shortage thus embodies a complex interplay between the processes of stellar evolution, nucleosynthesis, and cosmic conditions. This discrepancy continues to spawn detailed investigations, with researchers working to refine models, gather observational data, and seek explanations that can reconcile the differences between theory and observation, providing deeper insights into the history of elements in our universe. There are compelling reasons to believe that particles beyond the standard model of particle physics may exist. The standard model itself has proven remarkably successful in explaining a wide range of phenomena and the fundamental particles that make up our universe. It describes 3 of the 4 fundamental forces: electromagnetic, weak, and strong interactions, but it is not a complete theory. There are several key areas that suggest additional particles may exist. One prominent area is the need to account for dark matter. Observations of galaxies and galaxy clusters reveal that most of the matter in the universe is not visible. It does not emit, absorb, or reflect electromagnetic radiation, leading scientists to propose the existence of dark matter. Many theories suggest that dark matter could be composed of yet unidentified particles, possibly weakly interacting massive particles or WIMPs. These proposed particles would interact minimally with normal matter, making them difficult to detect, but their existence could explain various cosmic phenomena. Another area where particles may extend beyond the standard model is in the quest for unifying all fundamental forces, including gravity. Theories such as string theory and various models of quantum gravity suggest that additional particles, such as gravitons, could exist. Gravitons are hypothetical particles that mediate the force of gravity, much like how photons mediate electromagnetic forces. Currently, gravity does not fit neatly within the framework of the standard model, leaving a gap that necessitates further exploration. Moreover, the discovery of neutrino oscillations implies that neutrinos have mass, which is not accounted for in the standard model. This has led physicists to explore the possibility of additional particles or mechanisms, such as right-handed neutrinos or Majorana fermions, that could help explain this phenomenon. Lastly, current experiments, including those conducted at the Large Hadron Collider, are actively searching for new particles and signals that could indicate physics beyond the standard model. These experiments look for supersymmetric particles, extra dimensions, and other possible signs of new physics. As research continues, the potential for discovering particles beyond the standard model remains a thrilling frontier in our understanding of the fundamental nature of the universe. Neutrino oscillations represent a fascinating phenomenon in the field of particle physics that reveals the complex behavior of neutrinos, which are among the most elusive particles in the universe. Neutrinos are produced in various processes, including nuclear reactions in the Sun, cosmic ray interactions, and during radioactive decay. What makes neutrino oscillations remarkable is that these particles can change their type, or flavor, as they travel through space. Neutrinos exist in 3 known flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor corresponds to a specific charged lepton, electron, muon, and tau, respectively. The phenomenon of oscillation occurs because the 3 flavors of neutrinos do not have the same mass. Although they are incredibly light, experiments have shown that neutrinos exhibit a small but measurable mass difference. This disparity causes different flavor states to propagate at different speeds, leading to the oscillation effect as neutrinos travel. The underlying mechanism of neutrino oscillations is deeply tied to the concept of quantum mechanics and the principle of superposition. When a neutrino is produced, it is actually a mixture of the 3 flavor states, each with a corresponding amplitude. As the neutrino travels, these amplitude components evolve differently due to their mass differences. Thus, as the neutrino propagates, the probability of detecting it as one flavor or another changes over time, leading to fully realized oscillations that can be observed as the neutrino travels through space. The implications of neutrino oscillations are profound. The discovery of this phenomenon has provided strong evidence that neutrinos have mass, a significant deviation from the original framework of the Standard Model, which assumed neutrinos were massless. This finding has prompted physicists to explore extensions of the Standard Model, such as incorporating additional types of neutrinos, the seesaw mechanism, and potential interactions with new particles. Ongoing research into neutrino oscillations plays a vital role in understanding fundamental questions about the universe, such as the nature of matter and antimatter and the evolution of the cosmos itself. Experiments conducted across various facilities continue to refine our knowledge of neutrino properties, offering insight into this mysterious and intriguing aspect of particle physics. Magnetic monopoles are hypothetical particles that would carry a net magnetic charge, analogous to how electric charge exists in particles like electrons and protons. The existence of magnetic monopoles has intrigued physicists for decades and raises profound implications for our understanding of magnetism and fundamental forces. In classical electromagnetism, magnetic fields are created by electric charges. However, every magnetic field observed comprises dipoles, which have both a north and a south pole. This leads to the question, what if there were individual particles that possessed only a single magnetic pole? The theoretical groundwork for monopoles was laid by physicists such as Paul Dirac in the early 20th century, who proposed that the existence of magnetic monopoles could explain the quantization of electric charge. Despite the theoretical predictions, direct experimental evidence for magnetic monopoles has yet to be found. Various searches have been conducted, particularly in high-energy physics experiments and cosmic ray studies, but no clear detection has confirmed their existence. However, some anomalies in experimental data and certain physical theories continue to suggest that monopoles might exist in specific conditions, such as in certain contexts of quantum field theory, or as features of grand unified theories that seek to merge the electromagnetic weak and strong forces. Furthermore, researchers have also explored magnetic monopoles in condensed matter physics. In certain materials, phenomena resembling monopole behavior can occur, such as in spin ice systems. These materials exhibit magnetic monopole-like excitations, leading to interesting insights into topological aspects of magnetic fields. Ultimately, while magnetic monopoles remain a tantalizing possibility, their existence has not yet been definitively established. The exploration of magnetic monopoles is an ongoing area of research in both theoretical and experimental physics, offering the potential to unveil new understanding in fundamental physics and deepen our comprehension of magnetic phenomena. The origin of matter-antimatter asymmetry, or the apparent imbalance between the amounts of matter and antimatter in the universe, is one of the most profound questions in cosmology and particle physics. According to theories, the Big Bang should have produced equal amounts of matter and antimatter, given that the fundamental laws governing their production are symmetric. However, observations reveal that the universe is predominantly composed of matter, with very little antimatter detected. One of the leading explanations for this asymmetry is the concept of baryogenesis, which involves processes in the early universe that favored the production of baryons, the type of particles that include protons and neutrons. Several conditions have been proposed that may have led to such an imbalance, consistent with the criteria established by the Russian physicist Andrei Sakharov in the 1960s. These criteria include the existence of processes that violated baryon number conservation, C symmetry, which stands for charge conjugation symmetry, and CP symmetry, which stands for combination of charge conjugation and parity symmetry. In particular, many theories explore interactions within particle physics that may create a preference for baryon creation over anti-baryon creation. For example, certain types of interactions, like those occurring in the weak nuclear force, have been shown to violate CP symmetry. This means that the laws of physics governing particle interactions may treat matter and antimatter differently, leading to an excess of matter over antimatter as the universe cooled following the Big Bang. Cosmological scenarios, such as the electroweak phase transition that might have occurred as the universe cooled from high temperatures, are also under scrutiny. During this period, if conditions were right, it could have allowed for further mechanisms that generated a surplus of baryons. Some models even consider the role of hypothetical particles, like those predicted in grand unified theories and supersymmetry, which may contribute to the matter-antimatter imbalance. Despite extensive research, the exact origin of matter-antimatter asymmetry remains an open question, prompting ongoing investigations in both theoretical and experimental physics. Various experiments, such as those taking place at particle accelerators and in astrophysical observations, aim to uncover evidence that could shed light on this fundamental mystery and help explain why we see a universe dominated by matter. The search for undiscovered symmetries in particle physics is an active and exciting area of research that holds the potential to broaden our understanding of the fundamental forces and particles in the universe. Symmetries play a crucial role in physics, helping to establish conservation laws and guiding the development of theories. While the standard model of particle physics successfully incorporates several well-known symmetries, such as gauge symmetry and Lorentz symmetry, there are several reasons to believe that deeper yet undiscovered symmetries could exist. One motivation for exploring undiscovered symmetries arises from limitations in the standard model itself. For example, the model does not incorporate gravity, nor does it adequately explain phenomena such as dark matter and dark energy, which together constitute the majority of the universe's energy content. Theories such as string theory and various grand unified theories propose additional symmetries that might unify the electromagnetic, weak and strong interactions under a single framework. These theories often require new symmetries that extend beyond what is currently known, potentially revealing new particles or interactions. Moreover, some researchers are investigating the possibility of symmetries related to additional dimensions. In string theory and related frameworks, it is suggested that the universe may have more spatial dimensions than the three we perceive. These extra dimensions could have associated symmetries leading to new physical phenomena that remain to be explored. Another area of focus is the relationship between particles, particularly the potential for symmetry between matter and antimatter. This could lead to insights regarding the puzzling matter-antimatter asymmetry observed in the universe. The discovery of new symmetries could help elucidate the mechanisms that resulted in a universe predominantly composed of matter. Furthermore, researchers are also looking at the implications of supersymmetry, an extension of the standard model that posits a symmetry between fermions and bosons. While no evidence for supersymmetry has yet been found, if discovered, it could hint at even more symmetrical relationships in the particle world. As experimental techniques become more advanced, such as with the Large Hadron Collider and upcoming observational technologies, the quest for undiscovered symmetries continues to inspire new theories and experimental approaches. Each potential symmetry uncovered could reshape our understanding of the fundamental components of the universe, revealing a richer and more complex tapestry of physics lurking just beyond current knowledge. At the highest possible energies, matter behaves in ways that push the boundaries of our current understanding of physics. These extreme conditions can be found in environments such as those created during high-energy particle collisions at facilities like the Large Hadron Collider, or in cosmic events like supernovae and gamma-ray bursts. As energy levels increase, the interactions of particles become increasingly complex and can lead to phenomena that challenge the principles of the standard model of particle physics. One significant outcome occurs when particles collide with energies nearing the Planck scale, which is approximately 10 to the power of 28 electron volts. At this scale, it is theorized that the effects of gravity become comparable to other fundamental forces, potentially leading to a unification of gravity with the electromagnetic, weak, and strong forces. Such conditions could give rise to the formation of mini black holes or even initiate processes related to quantum gravitational effects, which have not yet been observed directly. At extremely high energies, particles can also undergo pair production, a process where energy is converted into mass, creating particle-antiparticle pairs. This means that under the right conditions, a photon with enough energy can produce a particle and its corresponding antiparticle. For example, a proton colliding with another proton at sufficient energy can lead to the creation of heavy quarks or even more exotic particles, expanding the particle zoo beyond what is typically found in everyday conditions. Additionally, the concept of color confinement in quantum chromodynamics becomes pivotal at high energy levels. As quarks and gluons are subjected to these extreme conditions, they can behave differently than in normal circumstances, potentially leading to the formation of a quark-gluon plasma. In this state, quarks and gluons are no longer confined within individual protons and neutrons, but can move freely, similar to a fluid. This state of matter is believed to have existed just after the Big Bang and is a focus of research in heavy ion collision experiments. As we explore these high-energy regimes, researchers aim to uncover new physics beyond the standard model, further elucidating the fundamental properties of matter and the forces that govern their interactions. The behavior of matter at incredibly high energies continues to be an area of active investigation, providing insights that may ultimately redefine our understanding of the universe. The cosmological constant is a fundamental concept in cosmology, introduced by Albert Einstein in the context of his general theory of relativity. It represents a measure of the energy density of empty space, or the vacuum energy, that contributes to the accelerated expansion of the universe. Despite its importance in understanding cosmic dynamics, the specific value of the cosmological constant remains one of the leading questions in modern physics, often referred to as the cosmological constant problem. One of the main issues is that theoretical predictions of the cosmological constant's value, based on quantum field theory, vastly differ from the observed value. Quantum field theory suggests that vacuum fluctuations of fields in empty space should create an enormous amount of zero-point energy, leading to a cosmological constant, many orders of magnitude larger than what is observed. This vast discrepancy is perplexing, as it implies that the vacuum energy must be fine-tuned to a remarkably small value to match observations of cosmic expansion. Various explanations have been proposed to address this mismatch. One possibility is that some yet unknown physical principles or symmetries might constrain the value of the cosmological constant. Some theories suggest that additional fields or particles could interact in a way that cancels out contributions to the vacuum energy, leading to the small effective value we currently observe. Another approach considers modifications to general relativity or alternative gravity theories that could alter the role of the cosmological constant in cosmic evolution. These theories may incorporate mechanisms that dynamically adjust the value of the cosmological constant over time, potentially responding to the changing energy content of the universe. The widespread acceleration of cosmic expansion detected in the late 20th century also raises intriguing questions about the interplay between the cosmological constant and dark energy. Dark energy is often used as a term to encompass mysterious forces driving this acceleration. Some researchers posit that the cosmological constant might not be a constant after all, but rather a dynamic entity that evolves over the history of the universe. Currently, ongoing observations from cosmological surveys and missions such as the European Space Agency's Euclid satellite and the Vera C. Rubin Observatory are aimed at probing the properties of dark energy and the cosmological constant. These efforts will contribute to deepening our understanding of why this fundamental parameter has its specific value and may unlock broader insights into the nature of the universe itself. The fundamental constants of physics, such as the speed of light, the gravitational constant and Planck's constant are considered to be constant within our current understanding of physics. These constants define the laws of nature and serve as the foundation for various scientific theories. However, the question of whether these constants are truly constant across all conditions in the universe and throughout its history is a topic of ongoing research and debate. In the context of known physics, fundamental constants are treated as invariant quantities. For instance, the speed of light in vacuum is universally regarded as a fundamental limit that does not change, which is central to the theory of relativity. Similarly, the gravitational constant is assumed to be constant in the equations governing the force of gravity. However, theories in cosmology and fundamental physics have raised intriguing possibilities about variations in these constants over cosmological timescales or in different regions of space. Some alternative theories propose that the constants might have varied in the early universe during certain high-energy events or phase transitions. For example, models involving extra dimensions or varying speed of light theories suggest that constants may not be uniform across the cosmos. Moreover, researchers have begun to investigate potential variations of constants by studying distant astronomical phenomena. Observations of quasars, supernovae, and the cosmic microwave background radiation can provide clues about the potential evolution of fundamental constants over time. Some studies have indicated minute deviations in the strength of fundamental forces, although these findings are often contentious and subject to intense scrutiny. Ultimately, while the fundamental constants are treated as constant in established theories, the quest for a deeper understanding of the universe keeps the door open to the possibility of their variation. As new experimental and observational data is gathered, scientists are refining their models and exploring the implications of both constant and variable fundamental quantities. This ongoing exploration underscores the dynamic nature of scientific inquiry, as our understanding of the universe may continue to evolve. The universe is often described as being finely tuned for the existence of complex structures such as galaxies, stars, planets, and ultimately life itself. This fine-tuning refers to the precise values of fundamental constants and conditions that allow for the development of structure and complexity we observe today. Alterations to these values, even slightly, could have profound consequences on the universe's ability to support such structures. One prominent example of fine-tuning is the strength of fundamental forces. The fundamental forces of nature, the electromagnetic force, strong nuclear force, weak nuclear force, and gravity, operating at their current strengths, create a delicate balance that allows matter to form stable atoms, which in turn can combine to create molecules and subsequently more complex structures. For example, if the strong nuclear force was slightly weaker, atomic nuclei could not hold together, preventing the formation of atoms heavier than hydrogen. Conversely, if it was slightly stronger, the universe would be dominated by heavy elements, leaving little room for the essential chemical diversity that supports life. Another factor contributing to the universe's fine-tuning is the initial conditions that prevailed during the Big Bang. The density of matter and energy, as well as the rate of expansion, were critical in determining the large-scale structure of the universe. A higher density could result in rapid gravitational collapse, while a lower density might prevent the formation of galaxies and stars altogether. The observed rate of expansion is also tuned to a remarkable precision, allowing for a universe that cools gradually enough for matter to aggregate into the complex structures we see today. The cosmological constant representing the energy density of space also plays a vital role in the evolution of the universe. Its specific value is critical in determining whether the universe ultimately collapses, remains flat, or continues to expand indefinitely. The current observations indicate that this constant is finely tuned to a value that allows for the accelerated expansion of the universe while facilitating the formation of structure over time. Lastly, some researchers explore the anthropic principle, which suggests that the universe must possess the properties necessary for the emergence of observers. meaning we should not be surprised to find ourselves in a universe that appears fine-tuned for life. While this principle provides one framework for understanding fine-tuning, it does not necessarily explain why specific constants hold the values they do. Overall, the fine-tuning of our universe raises deep questions about fundamental physics and the nature of reality. While ongoing research continues to investigate these issues, the intricate balance of conditions and constants that permit the existence of complex structures adds a layer of wonder to our understanding of the cosmos. The possibility of life existing with different values of fundamental constants is a profound question that intersects the fields of physics, astrobiology, and philosophy. While our understanding of life is grounded in the specific conditions of our universe, particularly the current values of fundamental constants, theorists often ponder whether life could arise under different conditions or in alternate universes with varying constants. The fundamental constants govern the interactions of the forces of nature, such as the electromagnetic, gravitational, and nuclear forces. Changing these constants would alter the properties and behaviors of matter, potentially impacting the formation of atoms, molecules, and larger structures necessary for life. For example, if the strength of the electromagnetic force were significantly different, it could affect chemical bonding, possibly preventing the formation of complex molecules like proteins and nucleic acids, which are essential for life as we know it. Similarly, variations in the gravitational constant could dramatically influence planetary formation, affecting conditions for stable orbits and climates. A weaker gravitational force might result in insufficient atmospheric pressure to support liquid water, which is considered necessary for life on Earth. Conversely, a stronger gravitational force could lead to planets that are too dense or have atmospheres that are inhospitable to life as we understand it. The implications of this question extend into the realm of exotic life forms that might arise under different physical conditions. Some scientists speculate that life could exist in forms vastly different from terrestrial biology, possibly based on alternative biochemistries or utilizing different solvents than water. For instance, researchers have proposed theoretical models of life based on silicon instead of carbon, as silicon shares some chemical properties with carbon, though it experiences limitations that make it less versatile. Moreover, the concept of a multiverse has emerged in theoretical physics, suggesting that there might be many different universes, each with its own set of physical constants. If such diverse universes exist, some may have the right conditions for forming life, albeit possibly in vastly different forms than those on Earth. Ultimately, while it is intriguing to contemplate the existence of life under different values of fundamental constants, the specifics and feasibility of such life remain largely speculative. The exploration of these questions can expand our understanding of life's adaptability and underscore the delicate balance of conditions that enable life in our own universe. As research continues in both the realms of cosmology and astrobiology, these intriguing possibilities will likely remain a focus for scientific inquiry and exploration. The question of whether the laws of physics vary across the universe is a topic of significant interest and debate in modern cosmology and theoretical physics. Currently, the prevailing view among scientists is that the fundamental laws and constants of physics are uniform throughout the observable universe. This assumption is based on extensive empirical evidence and the success of the Standard Model of particle physics and general relativity, which accurately describe a wide range of phenomena across different cosmic scales. However, some theories and observations propose that the laws of physics may not be entirely constant. For instance, certain models in cosmology suggest that the laws might have been different in the early universe, particularly during events such as the Big Bang or phase transitions that occurred shortly afterward. In these scenarios, the fundamental constants might have taken on different values in the extreme conditions present during those times. Additionally, the concept of a multiverse posits the existence of multiple, perhaps infinite universes, each potentially governed by different physical laws or constants. These universes might vary widely in their physical manifestations, leading to diverse forms of matter, forces, and possibly even life. While the multiverse theory is fascinating, it is still highly speculative and lacks direct empirical evidence to confirm its existence. In recent years, researchers have sought to investigate potential variations in fundamental constants over cosmic timescales. For instance, studies examining the light from distant quasars have looked for possible changes in the fine structure constant, a fundamental parameter related to electromagnetic interactions. While some findings have suggested slight variations, these results are controversial and subject to ongoing scrutiny. Another approach involves examining the possibility of spatial variations in physical laws. Some researchers have explored scenarios in which constants, such as the gravitational constant or the cosmological constant, might differ from one region of space to another. Such variations could arise in contexts that extend beyond our current understanding of physics. While the prevailing belief is that the fundamental laws of physics are consistent across the observable universe, there are intriguing avenues of research investigating the possibility of variations. These questions continue to inspire theoretical exploration and observational studies, pushing the boundaries of our understanding of the universe's underlying principles. As our knowledge of fundamental physics evolves, the possibility of discovering new insights into the uniformity, or lack thereof, of physical laws remains an exciting frontier in scientific inquiry. Beyond the observable universe lies a realm that is not accessible to observation and is largely unknown, yet it captures the imagination of scientists and cosmologists alike. The observable universe is defined by the region of space from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. This means we can observe galaxies and cosmic events up to a distance of about 13.8 billion light-years. However, space itself has been expanding since the Big Bang, meaning there are regions of the universe that are beyond our observational capabilities. One possibility for what lies beyond the observable universe is simply more of the same universe we can see. The universe is thought to be homogeneous and isotropic on large scales, suggesting that structures like galaxies, clusters, and voids are likely to continue beyond our current observational limits. The same physical laws and constants we observe should apply, leading to a vast extension of the universe that we can only infer. Another intriguing concept is the possibility of a flat or infinite universe. If the universe is indeed infinite, then beyond the observable universe there would be an endless expanse of space that continues infinitely in all directions. Given this scenario, distant regions could harbor the same types of structures, stars, and galaxies seen within our observable limits. The multiverse theory proposes a different perspective on what exists beyond the observable universe. This theory suggests that our universe might be just one of many separate universes, each potentially governed by different physical laws or constants. In this framework, different pocket or bubble universes could exist with unique properties, including varying dimensions, forces, and even fundamental constants. The nature of these universes could be vastly different from our own, leading to different forms of matter, energy, and possibly even different types of physical processes. Moreover, the fabric of spacetime itself may hold mysteries beyond the observable universe. Hypothetical concepts, such as string theory and dimensions beyond the familiar three-dimensional space and one-dimensional time, suggest that our understanding of reality could be expanded to include additional dimensions that are not directly observable. Ultimately, while we cannot directly observe what lies beyond the observable universe, theoretical explorations continue to drive our understanding of the cosmos. These ideas serve to remind us that the universe is vast and rich with possibilities, inviting scientists to engage in ongoing inquiry about the nature of existence itself and what mysteries might still remain to be unveiled. The prospect of observing the universe's first stars often referred to as population 3 stars, is one of the intriguing challenges in modern astrophysics. These stars are thought to have formed from primordial gas, primarily composed of hydrogen and helium, shortly after the Big Bang, approximately 100 million to 400 million years after the event. Due to their unique characteristics, including likely being massive, short-lived, and composed almost entirely of the primordial elements, the first stars could provide essential insights into the early universe and the processes that led to the formation of galaxies and complex structures. Observing these ancient stars directly poses significant challenges. One of the primary issues is that they are located very far away, often at redshifts beyond 6, meaning the light we would need to observe them has been traveling for billions of years. As a result, the light from these stars is very faint and much dimmer than that of more contemporary stars, making detection with current telescopes difficult. However, advancements in technology and observational techniques offer hope for the future. Next-generation space telescopes such as the James Webb Space Telescope, planned to launch in the coming years, are designed to observe the infrared wavelengths of light. These wavelengths allow astronomers to penetrate the dense clouds of dust and gas that can obscure observations in optical ranges. As these advanced instruments come online, they may be able to detect the faint signatures of the first stars or the ionizing radiation from their formation, which played a critical role in the ionization of the universe. In addition to direct observations, astronomers are also exploring indirect methods to study the first stars. This includes examining the cosmic microwave background radiation, which provides clues about the conditions prevailing in the early universe. Simulations and models that mimic the formation and behavior of population 3 stars can also yield valuable insights into their characteristics and the impact they had on their environments. While the prospect of directly observing the universe's first stars remains a formidable challenge, ongoing advancements in technology and innovative observational strategies make it a tantalizing possibility for the future. The study of these primordial stars would deepen our understanding of the early universe, shedding light on the processes that led to the development of galaxies, stars, and the complex cosmic tapestry we see today. Probing the universe's dark ages is an essential aspect of understanding cosmic history, specifically the period following the Big Bang, when the universe expanded and cooled, but before the first stars began to form. This epoch, roughly between 400,000 years and about 1 billion years after the Big Bang, is termed the Dark Ages, because during this time, the universe was devoid of bright sources of light, making it challenging to observe using traditional methods. 2. One of the primary methods of probing this period is through the study of the cosmic microwave background radiation, or CMB. The CMB is the afterglow of the Big Bang, released when the universe cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This event allowed photons to travel unimpeded through space, providing a snapshot of the universe when it was about 300,000 years old. By analyzing the CMB's temperature fluctuations and polarization patterns, scientists can gather information about the conditions during the universe's formative years, laying the groundwork for understanding the subsequent dark ages. Another critical approach is the exploration of high redshift astronomical objects. As light from distant galaxies and quasars takes billions of years to reach us, observing these objects allows astronomers to peek back in time. By studying objects at redshifts greater than 6, scientists can infer conditions of the universe during the dark ages. The light emitted by early stars and galaxies can provide insights into when the first luminous sources emerged and how they affected their surroundings. One promising observational target is the detection of the first stars, known as population 3 stars, which are believed to have formed from primordial gas composed mainly of hydrogen and helium. Understanding the formation and impact of these stars will provide crucial information about the reionization epoch, the period when the universe transitioned from the Dark Ages to an ionized state filled with light. Upcoming observatories, such as the James Webb Space Telescope, are designed to probe this era by observing the infrared wavelengths that could reveal significant information about early stars and galaxies. Another technique involves searching for signatures left in the intergalactic medium during the Dark Ages, specifically through a process called 21 centimeter hydrogen mapping. This method takes advantage of the hyperfine transition of neutral hydrogen, which emits radiation at a frequency of 21 centimeters. By mapping variations in this signal on large scales, astronomers can glean insights into the density and temperature of the hydrogen gas filling the universe during the Dark Ages, revealing details about cosmic structure and the conditions leading to the first galactic formations. The combination of these observational and theoretical approaches helps create a more comprehensive understanding of the Dark Ages. As technology advances and new observational tools come into play, scientists continue to refine their models and expand our understanding of this enigmatic period in cosmic history. Ultimately, probing the universe's dark ages will illuminate many fundamental aspects of the universe's evolution and formation. The ultimate limits of astronomical observations are determined by a combination of physical, technical, and philosophical factors. As we strive to explore the cosmos, understanding these limits can help guide the development of new technologies and observational strategies. One of the primary physical limits arises from the finite speed of light. Because light takes time to travel across vast distances, astronomical observations are always effectively peering back in time. The farthest objects visible to us are those whose light has taken billions of years to reach Earth. This means that our observations become limited to events that occurred in the past, and there is an effective observable universe boundary that defines the limit of what we can detect. As such, we cannot see beyond the cosmic horizon, which is about 46 billion light-years away today, because light from regions beyond this distance has not had enough time to reach us since the Big Bang. Another significant limit relates to the increasing distance from which we observe objects. As objects in the universe recede from us, especially due to the universe's expansion, their light becomes red-shifted, moving toward longer wavelengths. Extremely distant galaxies may be so red-shifted that they fall outside the observable range of current instruments, making them difficult or impossible to detect. Additionally, at great distances, objects become incredibly faint, posing challenges in distinguishing them from background noise. Technical constraints also play a crucial role in pushing the boundaries of astronomical observations. The sensitivity, resolution, and dynamic range of telescopes and detectors dictate how much light they can gather and how finely they can resolve details. Current telescopes and instruments are limited by technological capabilities such as the size of mirrors and the effectiveness of detectors, which constrain our ability to observe faint or closely spaced objects. Moreover, atmospheric interference poses a limitation for ground-based observations. The Earth's atmosphere absorbs and scatters certain wavelengths of light, particularly in the ultraviolet and infrared ranges, leading to blurring and loss of clarity in images. While advancements in adaptive optics and the construction of observatories in space have mitigated these issues, observing from space comes with its own set of challenges, including the need for robust instruments that can operate in extreme conditions. Finally, philosophical questions of observational limits arise when considering the nature of reality. Concepts such as the cosmic horizon and the potential existence of multiverses prompt questions about whether there may be aspects of the universe forever beyond our observational reach. For example, regions influenced by cosmic inflation or the possibility of other universes with different physical laws may remain inaccessible to any form of detection. As technology progresses and new observational techniques are developed, these limits may be pushed further back. Yet the fundamental laws governing light, the universe's expansion, and the constraints imposed by our environment will always define the ultimate boundaries of our astronomical observations. Understanding these limits is vital to the ongoing quest to unravel the mysteries of the cosmos. Detecting gravitational waves from the early universe is a significant challenge in modern astrophysics, but holds great potential for deepening our understanding of cosmology and fundamental physics. Gravitational waves, predicted by Albert Einstein's general theory of relativity, are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. However, the early universe, particularly during moments such as the Big Bang, inflation, and phase transitions, would have produced its own distinct gravitational waves. One of the primary strategies for detecting these gravitational waves involves observing the cosmic background gravitational radiation that would have been generated during the extreme conditions of the early universe. Events like cosmic inflation, a rapid expansion of the universe occurring just after the Big Bang, are theorized to have generated a stochastic background of gravitational waves. If these waves carry imprints of the fluctuations from inflation, their detection could provide valuable insights into the dynamics of the early universe. To detect these gravitational waves, scientists utilize large-scale observatories designed for high sensitivity. Current ground-based detectors, such as the Laser Interferometer Gravitational Wave Observatory and the Virgo collaboration, excel in identifying gravitational waves from relatively nearby astronomical events, like binary black hole mergers. However, these facilities are generally sensitive to frequencies above 10 Hz and are not optimized for the low-frequency waves generated in the early universe. I see. In response to this challenge, scientists have proposed advanced observatories that will be sensitive to lower-frequency gravitational waves. One notable project is the Laser Interferometer Space Antenna, a planned space mission that aims to detect gravitational waves in a frequency range from below 1 MHz to about 1 Hz. By employing a constellation of spacecraft separated by millions of kilometers, LISA will be able to measure the minute variations in distance caused by passing gravitational waves, making it well suited for detecting low-frequency signals from the early universe. Another promising avenue for detecting gravitational waves from the early universe is through observations of the cosmic microwave background radiation, particularly its polarization. The inflationary gravitational waves would create a distinctive pattern known as B-mode polarization in the CMB. Experiments such as the BICEP and Planck missions have been focused on measuring these polarization patterns, and future endeavors like the Simons Observatory could provide further insights into this potential signal. In conclusion, while the detection of gravitational waves from the early universe remains an ongoing pursuit, advancements in technology and the development of specialized observatories hold the promise of unveiling the cosmic events that shaped the very foundation of our universe. These gravitational waves could provide a unique window into the conditions of the early cosmos, helping us to better understand inflation, phase transitions, and the fundamental nature of space-time itself. We've barely scratched the surface of what we don't understand about the universe. Think about it. Dark matter, quantum entanglement, the nature of time. These aren't just scientific puzzles, they're gaps in our fundamental grasp of reality. And for every mystery we've discussed, there are likely dozens we haven't even recognized yet. Science isn't just about answers. It's about pushing the boundaries of what we can ask. Today's cutting-edge theories might seem as quaint to future physicists as geocentrism does to us now. So what's next? What paradigm-shifting discoveries await us? What assumptions are we making that future generations will overturn?